Hi there, and welcome back. You've heard us talk a lot about programming and automation. This course focuses on a slightly different aspect: how to keep track of the different versions of your code and configuration files using version control systems, or VCSs. These are tools that everyone in IT can benefit from, even if it's not just for programming or automation itself. It will allow us to easily roll back when mistakes happen and also help us collaborate with others. You might have already heard of version control systems in the context of managing configuration files or maintaining the source code of programs and scripts. In this course, we'll introduce you to a popular VCS called Git and show you some of the ways you can use it. We'll also go through how to set up an account with a service called GitHub so that you can create your very own remote repositories to store your code and configuration. By the end of this course, you'll be able to store your code's history in Git and collaborate with others in GitHub, where you'll also start creating your own portfolio. Nowadays, lots of employers will ask to see your GitHub portfolio when you're interviewing for IT roles. GitHub portfolios give companies an idea of what projects you've worked on and what kind of code you can write. This course will help you get yours set up. I'm Kenny Suleiman, and I'll be your instructor for this course. I work as a technical program manager for Android system health and velocity. In my role, I work with engineering and leadership to ensure that we launch healthy and stable Android devices for all of our users. I'm thrilled to be your instructor for this course. As a technical program manager, my main challenge is making sure that everyone involved is aligned on a shared vision. To ensure our project's a success, my team creates a narrative, figures out all the stakeholders, and makes sure everyone is on the same page. After all that comes the hardest part: executing the project to completion. To do that, it's essential we have a version control system where each engineer can store and share the code they create. This lets us track different revisions, roll back problematic changes, and work together effectively. Before we jump in, I'd love to take a quick moment and share why I'm so excited to be here with you, participating in this program. Ever since I was young, I've always been obsessed with new technology. I used to fix my friends' old broken computers, for a small fee of course, and would spend hours trying to mod my old video game systems so I could squeeze some more fun out of my favorite games. So once I found out I can get paid to work on computers and cool gadgets for a living, I was sold. There was only one problem. When I started my first IT job, there were very few people that, looked like me. As I started to move up the ranks, this disparity only grew. I quickly realized that this isn't only an IT support issue, but something the entire tech industry is struggling with. The representation problem is something I'd like to solve one day. And the only way I can do that is to lead by example, share my knowledge, and help as many people as I can achieve their goals. And who knows? Maybe one day someone will take the information they've learned here and use it to change the world. Psst, remember me when you're famous. Anyway, enough about me. Let's get back to the course. There's a lot to learn with Git and version control. We'll break it down step by step so you can fully understand how it works and why it's so useful in your IT role. Whether you're an IT support specialist, a systems administrator, or looking to expand your skills towards other roles in IT. Throughout this course, you'll learn about Git's core functionality so you can understand how and why it's used in organizations. We'll look at both basic and more advanced features like branching and merging. We'll demonstrate how having a working knowledge of a VCS like Git can be a lifesaver in emergency situations or when debugging. And we'll explore how to use a VCS to work with others through remote repositories like the ones provided by GitHub. To do all this, and so you can follow along with the exercises in these videos, you'll need to install Git on your computer. This will also let you interact with GitHub and upload your code there. For the examples in this course, we'll show a bunch of different Python scripts. While you don't need to know any Python to use Git, we do recommend that you have a basic knowledge of the language so that you can understand the examples and the functionality we'll be demonstrating. If you've done the courses on Python in this program, you're covered. If you haven't, that's okay. but you might need to freshen up your Python skills to follow some of our examples. Also, since all the scripts will use Python 3, you'll need to have Python 3 installed in your computer to run them. For our examples, we're going to use a Linux computer interacting with the Linux command line through the most common command line tools. Again, if you joined us for the Python courses, you're already familiar with all these concepts. If you're jumping into this program with this course, you might benefit from reviewing some of the most basic Linux commands. Please remember, some of these topics and videos are a little complex, so they might not 100% sink in the first time around. That's totally natural. Take your time and review any content that's not completely clear. You'll get the hang of it eventually. All right, we're ready to get started learning about Git and version control. Let's get to it. When you work in IT, you manage information across a lot of different files. You write automation scripts that might evolve over time. For example, you might add new features to your script or take into account additional conditions or modify the scope of systems where the script will be executed. You also manage configuration related to your infrastructure, like the default settings on an application or the IP addresses assigned to the computers in your fleet. This information changes over time as the security requirements increase, the fleet grows, or new versions of software gets deployed. When trying to manage change in IT, it's super important to have detailed historical information for your organization's configuration files and automation code. This lets the administrator see what was modified and when, which can be critical to troubleshooting. It also provides a documentation trail that will let future IT specialists know why the infrastructure is the way it is. And it provides a mechanism for undoing a change completely. This way, we don't have to undo changes from memory, and there's less chance of human error. We'll see this in action when we talk about rollbacks. Imagine this. Your team has added a new feature to a script that checks the health of all the computers that you're responsible for. The new check verifies that the firmware of the computer, also known as the UEFI, is updated to the latest version. When you roll this out, you suddenly realize that half the computers now say they're broken. After some investigation, you discover that the check needs to take into account different computer models. You might be tempted to do a quick code fix, push it to the affected machines right away, especially if it seems like an easy fix. But more often than not, quick fixes include their own bugs because we don't take the time to test the new code properly. So, after the first fix, you might end up doing a second or even third emergency push until things are really working correctly. To avoid these headaches, you can use a version control system to easily roll back your code to the previous version. Since you know that this version was working correctly before the change was made, it would be safe to go back to that one until you've had time to fix the code, run some tests, and make sure everything works correctly for all machine models. By releasing code only after properly testing, you avoid having to push quick fix after quick fix. Version control systems let us do this and much more. They're crucial to maintaining a healthy code base for all kinds of IT resources, and for letting multiple people collaborate on the same coding projects together. We're now going to take our first steps to learning this new tool, which will let us keep track of the changes that we make to our scripts, our configuration files, and any other kind of documents that need to be tracked. We'll start by looking at what people tend to do when they don't know about version control, and then check out some related tools, like diff and patch. Once we have a clear idea of why we need proper version control, we'll jump into our first Git experience. We'll talk about what Git is and how it does what it does. To follow along, you'll need to install Git locally on your machine and learn how to use it from the command line. If this sounds a bit scary, don't panic. We'll guide you along the way and you'll be using it in no time. Once you have Git installed in your computer, we'll do an overview of the basic Git workflow, which will let you start keeping track of your scripts. So, are you ready to start taking control of your code? Here we go. Have you ever worked on a project that was developing over time, so you occasionally created copies of the work in case you wanted to go back to an earlier version? Maybe you were working in a team, and every day you'd email a part of the work to the rest of the team. And then the other members on your team would add their own work and send it out to the whole team too. Or maybe you've worked on a very complex project that kept changing directions, and you felt that some of the things that got removed one day might have to be added later on. So anytime you were about to delete a significant part, you made a copy of the whole thing just in case. If any of this sounds familiar, you've already worked on the most primitive form of version control, keeping historical copies. These copies let you see what the project was like before and go back to that version if you end up deciding that the latest changes were wrong. They also let you see the progress of the changes over time, and maybe even help you understand why a change was made. We say that this is primitive because it's very manual and not very detailed. First, you need to remember to make the copy. Second, you usually make a copy of the whole thing even if you're only changing one small part. And third, even if you're emailing your changes to your colleagues, it might be hard to figure out at the end who did what, and more importantly, why they did it. But that said, the principle behind version control is the same. It lets us keep track of the changes in our files. These files can be code, images, configuration, or even a video editing project, whatever it is you're working with. Throughout this course, we'll see the many ways that Git helps us keep track of our changes, and also how we can use it to collaborate with others or revert changes. We'll use a bunch of terms that have special meanings in the world of version control. But don't let those intimidate you. In the end, all we're doing is having better control over our historical copies. So, say you have two copies of the same code made at different points in time. How can you compare them? Hop on over to the next video and you'll find out. Imagine you had two copies of some code and you wanted to see what the difference was between them. How would you do it? You could open both files in an editor side by side, look at one, then look at the other to spot the differences, but that's super error prone. We're human, and by comparing with our eyes, we're bound to miss some differences, right? Fortunately, there's a better way. You can use some nifty tools that will do this automatically. We can use the diff command line tool to take two files, or even two directories, and show the differences between them in a few formats. Let's check it out with an example. We have two files, rearranged1.py and rearranged2.py, which contain two different versions of the same function. Let's take a look at them using cat. Can you spot the difference? Maybe you can, but it's not super obvious. Let's use the diff command so that we don't have to strain our eyes trying to spot it. When we call the diff command, we get only the lines that are different between two files. It's much easier to find the difference when we just have two lines, right? See the symbols at the beginning of each of those lines? The less than symbol tells us that the first line was removed from the first file, and the greater than symbol tells us that the second line was added to the second file. In other words, the old line got replaced by the new one. In this example, we had one line that was replaced with a new one. This is a common change when modifying code, but not the only possibility. Let's check out another example. Here, there are more changes going on. We can see that diff splits the changes in two separate sections. The section that starts with 5c5,6 shows a line in the first file that was replaced by two different lines in the second file. The number at the beginning of this section indicates the line number in the first and second files. The C in between the numbers means that a line was changed. The section that starts with 11a 13,15 shows three lines that are new in the second file. The A stands for, you guessed it, added. But that block looks a bit strange, doesn't it? It seems like we're adding a return and an if condition, but no body for the if block. What's up with that? To understand this better, we can use the -u flag to tell diff to show the differences in another format. Let's check that out. This unified format is pretty different from the one that we saw before. It shows the changed lines together with some context, using the minus sign to mark lines that were removed and the plus sign to mark lines that were added. The extra context lets us better know what's going on with the change that we're diffing. We can see that the new file actually has a completely new if block that's part of a chain of conditionals that looks very similar. And that's why with the diff output that we saw before, it was a little confusing which lines had been added. There are a lot of tools out there to compare files. Diff is the most popular one, but not the only one available. For example, wdiff highlights the words that have changed in a file instead of working line by line like diff does. To help us even more, there are a bunch of graphical tools that display files side by side and highlight the differences by using color. Some examples of this include Meld, kdiff3, or vimdiff. We can use these tools to give better context to the changes that we see. Okay, we've talked about how we can see differences between two files. Now, how can we use those differences to apply changes? That's coming up in the next video. Imagine a colleague sent you a script with a bug and asked you to help fix the issue. Once you understood what was wrong with the script, you could describe to them what they need to change. Something like, well, you can only return values inside functions. I think you meant to use sys.exit instead. Also, you're converting to gigabytes twice, so your script will always fail. But this could still be hard for them to understand if the code was complex. To make the change clear, you could send them a diff with the change so that they can see what the modified code looks like. To do this, we typically use a command line like diff-u, old file, new file, greater than, change.diff. As a reminder, the greater than sign redirects the output of the diff command to a file. So with this command, we're generating a file called change.diff with the contents of diff-u command. By using the -u flag, we include more context, which helps the person reading the file understand what's going on with the change. The generated file is usually referred to as a diff file, or sometimes a patch file. It includes all the changes between the old file and the new one, plus the additional context needed to understand the changes and to apply those changes back to the original file. Now, say you're the one receiving a diff file with a change, and you want to apply it to a script you wrote. You could read the diff file you received carefully and then manually go through the file that needs to be changed and apply the modifications. But that sounds like a lot of manual work that could be automated, don't you think? Well, it sure is. There's a command called patch to do exactly this. Patch takes a file generated by diff and applies the changes to the original file. Let's check this out in an example. Say we have a small script that checks whether the computer is under too much load, like this one. This script uses the psutil module to check the percentage of the CPU that's currently in use. When the load is above a threshold, in this case 75%, it prints a message with an error. When it's under the threshold, it says that everything's okay. Now, we've shared this script with a few colleagues, and one of them tells us that the script doesn't work correctly. Even if a computer is completely overloaded, the script will say that everything's okay. Our colleague is so helpful that they sent us a diff with the fix for our problem. Let's check that one out. We can see that our colleague made two changes. They added a 1 as a parameter to the CPU percent function, and they added a debugging line that prints the value returned by the function. Our colleague explains that by calling the CPU percent function without a parameter, we were not averaging over a period of time, and so the call always returns 0. So, we have the diff file, and we want to apply it to our script. How do we do that? We'll use the patch command. We'll pass the name of the file that we want to patch, in this case, cpuusage.py, as the first parameter to the command. And then we'll provide the diff file through standard input. Do you remember how to do that? We'll use the less than symbol to redirect the contents of the file to standard input. Let's check this out. So, we told patch to apply the changes that come from cpuusage.diff to our cpuusage.py file. We get one single line that says the file was patched, which means that we've successfully applied the changes. Let's verify that by looking at the contents of our script. Nice! We see that our file was modified with the changes that we got from our colleague. The CPU% function is being called with a parameter of 1, and the debugging line is printed. Once we're happy with the script, we could remove the debugging line. But for now, we'll leave it in there. You might be wondering, why go through all this trouble diffing and patching and not just send the whole file instead? There are a few reasons for this. The main reason is that the original code could have changed. In our example, it's possible that the code our colleague was using to prepare the fix wasn't the latest version. By using a diff instead of the whole file, we can clearly see what they changed, no matter which version they were using. The patch command can detect that there were changes made to the file and will do its best to apply the diff anyways. It won't always succeed, but in many cases it will. Another reason is structure. In this case, we're patching a single small file, but sometimes you might be modifying a bunch of large files inside of a huge project. Say you were changing 4 files in a project tree that contain 100 different files, arranged in different directories according to what they do. If you were to send the whole files, you'd need to specify where those files were supposed to be placed. As we called out, we can diff whole directory structures, and in that case, the diff file can specify where each change file should be, without us having to do any manual juggling. Cool, right? Okay, great work. We've now seen how to generate diff files and how to apply their contents with the patch command. In the next video, we'll put all this together to look at a real-world example of how to use diff and patch. Imagine this. A colleague is asking our help with fixing a script named disk.usage.py. The goal of the script is to check how much disk space is currently used and print an error if it's too little space for normal operation. But the script is currently broken because it has a few bugs. We'll help our colleague fix those bugs to demonstrate how to use diff and patch. Before we change anything, let's make a couple copies of the script. We'll add _original to one copy, which we'll keep unmodified and use for comparison, and _fix to the other copy, which we'll use to prepare our fix. Okay, now that we have our copies, we'll edit the _fix version and actually fix it. This file has a bunch of code. Before we try to understand what it does and what's wrong with it, let's execute it and see what we get. The Python interpreter isn't too happy. It's complaining that there's a return outside of function. And if we look at the code, we can clearly see that there's a return that's not inside any function. You might remember that in Python, we can only use return statements inside functions. So how do we fix this? There's a couple options. We could turn the current code into a function and then call that function from the main part of our script, or we could use sys.exit to make the return number the exit code of our script, which is the code that causes a program to exit with the corresponding exit value. For now, let's go with the second option. Okay, we've made the change. Let's execute this new version of our script. Darn. We fixed the syntax error, but now the script is telling us we don't have enough space on our disk. But we know that we actually do have some free space, right? What's up with that? If you look closely at the code, you might notice that the script is converting to gigabytes twice. The function call to check disk usage is passing 2 times 2 double star 30. You might remember that the double star operator is used to calculate powers. In this case, 2 to the power of 30, which is how many bytes are in a gigabyte. So, this would be 2 gigabytes. But that'd be if the check disk usage function was expecting a value in bytes. If we look at the code of the function, we can see that it's already dividing the amount of free bytes by 2 to the power of 30. So, in other words, we're doing the gigabyte conversion twice, once when calling the function and once inside the function. We need to get rid of one of them. Let's change how we call the function. Okay, let's try it out again. Woohoo! It works now. Okay, now we need to send a fix to our colleague so that they can fix their script. To do that, we'll use the technique we just learned to generate a diff file, like this. Let's check the contents of the diff using the cat command. Awesome! This seems to have what we want. So this is what we need to send to our colleague to have them patch their file. How would they do that? They would run the patch command like this. By calling patch with the diff file, we've applied the changes that were necessary to fix the bugs. Let's check that disk usage.py now executes successfully. Success! So we've now seen how we can look at differences between files, generate diff files to gather together our changes, and then apply those changes using patch. But this is still a very manual process, where version control systems can really help. But before we jump into that, in the next cheat sheet, you'll find a summary of the commands we just covered. So check that out and then head over to the practice quiz to make sure you've got a grasp on all this. We've seen up till now how we can use existing tools to extract differences between versions of files and apply those changes back to the original files. Those tools are really useful, but most of the time we won't be using them directly. Instead, we'll use them through a version control system, or a VCS. A version control system keeps track of the changes that we make to our files. By using a VCS, we can know when the changes were made and who made them. It also lets us easily revert a change if it turned out not to be a good idea. And it makes collaboration easier by allowing us to merge changes from lots of different sources. At first look, a version control system can seem like a complicated, possibly intimidating tool. But if you look closer, you'll see that it's really just a system that stores files. However, unlike a regular file server, which only saves the most recent version of a file, a VCS keeps track of all the different versions that we create as we save our changes. There are many different version control systems, each with their own implementation and with their own advantages and disadvantages. But no matter how the VCS is implemented internally, they all let us access the history of our files. They let us retrieve past versions of the file or a directory and see who changed which files, how each file was changed, and when the file was changed. On top of this, we can make edits to multiple files and treat that collection of edits as a single change, which is commonly known as a commit. A VCS even provides a mechanism to allow the author of a commit to record why the change was made, including what bugs, tickets, or issues were fixed by the change. This information can be a lifesaver when trying to understand a complex series of changes or to debug some obscure issue. So be sure to record this extra info in your commits to be truly committed to better code. In any organization that produces software, a VCS is a key part of managing the code. Files are usually organized in repositories, which contain separate software projects or just group all related code. If there's a lot of people involved in developing software, some developers may have access to only some of the repositories. A single repository can have as little as one person using it, and it can go up to thousands of contributors. And, as we called out earlier, a version control system can be used to store much more than just code. We can use it to store configuration files, documentation, data files, or any other content that we might need to track. Because of the way tools like diff and patch work, a VCS is especially useful when tracking text files, which can be compared with diff and modified with patch. We can also store images, videos, or any other complex file formats in a VCS, but it won't be easy to check the differences between versions when comparing these file formats. And it might not be possible to automatically merge changes made to older versions of a file. All right, you now have a basic idea of what a version control system is and how it works. You might be asking yourself, do I really need this? Can't I just keep making backups of my code once in a while? We'll answer that in our next video. At first glance, using a VCS might seem like a lot of work for an IT specialist to set up and learn. It might especially seem like overkill if you're the only member of your IT team that writes code, or maybe even the only member, period. So can a VCS help even if you don't need to share your scripts or collaborate on them with others? The short answer is yes. A VCS can be invaluable even in a one-person IT department. A VCS stores your code and configuration, and it also stores the history of that code and configuration. A version control system can function a lot like a time machine, giving you insights into decisions of the past. Whenever you write a commit message after making a change, it's as if the current version of yourself is explaining your decisions to a future you, or, others who might work on the same scripts and configurations in the future. This can help you avoid finding yourself staring at a piece of code that you or someone else wrote 3 months ago and puzzling over how it works or even why it exists. With a VCS, you can view, track, and select snapshots from the history of your project, so nothing you do is lost. And since we can use a VCS to store both code and configuration files, we can make the overall IT systems more scalable and reliable. For example, let's say you've stored the DNS zone file for your company in a VCS. And in case you don't remember, a DNS zone file is a configuration file that specifies the mappings between IP addresses and host names in your network. When you update the zone information, always use good explanatory commit messages. That way, you'll have access to meta information about your new IP addresses and host names present in the zone file, like when they were added and for what purpose. If anything breaks after you add a new entry, you can rely on the VCS to tell you what the file looked like before the change. You can then revert to the old version quickly so you can fix the problem fast and figure out what went wrong later. This functionality enhances the reliability of systems you operate. Because of the audit trail provided by the VCS, you know exactly what version of the zone file to roll back to, which reduces the time it takes to fix the problem. It's generally better to quickly roll back first and stop errors before spending time figuring out what went wrong. You can code up the fix after the bleeding is stopped. Figuring out the bug might take up valuable time, or worse, your first attempt at a solution could have its own bugs. Let's look at a different example. The configuration for a DHCP daemon can be replicated in 2 or more machines, where one acts as a primary server and the other one acts as a standby machine. The standby machines won't do much while the primary is up. But if the primary goes down for any reason, a standby machine can become primary and start responding to DHCP queries. For this to work, the configuration files on all machines need to be identical. This is because the DHCP protocol doesn't provide a way for standby machines to get an up-to-date version of the configuration files in the way DNS does. To deal with this, we can keep the up-to-date version of the DHCP configuration in a version control system and have the machines download the configuration from the VCS. This means all the machines will have the exact same files. That's already handy enough, but after using it for a while, you're bound to see other benefits. Say you get an urgent alert over the weekend, telling you that your DHCP server isn't responding to any queries. You look at the history of the changes and you find that one of the changes added on Friday evening included a duplicated entry, causing the server to misbehave. By using a VCS, you can easily roll back the change and have the servers back to health in no time. You might come across a second unexpected benefit when it's time to replace the server with a new one. By having all the server configuration in a version control system, it's much easier to automate the task of deploying a new server. Are you starting to see how useful version control systems can be? You might even be thinking of some situations when having your files in a VCS would have saved you a few headaches. As we said in the beginning, in this course, we'll use Git, which is one of the most popular version control systems in use today. Up next, we'll learn a bit about the history of Git and what makes it so special. Git is a VCS created in 2005 by Linus Torvalds, the developer who started the Linux kernel. Git is a free, open source system available for installation on Unix-based platforms, Windows, and Mac OS. Linus originally created Git to help manage the task of developing the Linux kernel. This was difficult because a lot of geographically distributed programmers were collaborating to write a whole bunch of code. Linus had some requirements for the way that the system worked and its performance that weren't being met by the VCS tools at the time. So he decided to write his own. Git is now one of the most popular version control systems out there and is used in millions of projects. Unlike some version control systems that are centralized around a single server, Git has a distributed architecture. This means that every person contributing to a repository has full copy of the repository on their own development machines. Collaborators can share and pull in changes that others have made as they need. And because the repositories are all local to the computer being used to create the files, most operations can be done really fast. If you want to collaborate with others, it usually makes sense to set up a repository on a server to act as a kind of hub for everyone to interact with. But Git doesn't rely on any kind of centralized server to provide control or organizations to its workflow. Git can work as a standalone program, as a server, and as a client. This means that you can use Git on a single machine without even having a network connection. Or you can use Git as a server on a machine where you want to host your repository. And then you can use Git as a client to access the repository from another machine, or even the same one. Git clients can communicate with Git servers over the network using HTTP, SSH, or Git's own special protocol. If you're curious about diving deeper into Git's architecture or communication protocols, we've put a link for more information in the next reading. So, you can use Git with or without a network connection. You can use it for small projects with like one developer or huge projects with thousands of contributors. You can use it to track private work that you can keep to yourself, or you can share your work with others by hosting the code on public servers like GitHub, GitLab, or others. Are you starting to see how powerful Git can be? When looking for information online, you might notice that the official Git website is called git-scm.com and wonder, what's the SCM at the end for? It's actually another acronym similar to VCS. It stands for Source Control Management. While both terms mean the same, we generally prefer VCS because, as we've called out already, these systems can actually be used to store much more than just source code. In this course, we chose Git for its popularity, multi-platform support, and robust set of features. As with most things in the IT world, though, there are plenty of other tools that can be used to accomplish the same task. There are other VCS programs like Subversion or Mercurial. Feel free to experiment with alternatives if you think another VCS might better serve your needs. But before we jump into how to use Git, let's go through another quick quiz to check that everything up until now is making sense. In this course, we'll cover many different things that you can do with Git. To follow along, you'll need to install Git on your computer. On top of this, we'll show you how to interact with Git through the command line. So, if you aren't yet already familiar with the command line, this is your opportunity to brush up. Our examples will be shown on a computer running Linux, but you can use Git on any operating system. There are versions of Git available for all popular operating systems. So, before we get any further, let's get Git installed on your computer. The first step is to check whether you already have it installed. You can do this by running git ---- version. If you're running a version number higher than 2.20, then you can just use that one. If you get an error message or an older version number, you'll need to install the current version. If you use a package management system like apt or yum on Linux, Chocolatey on Windows, or Homebrew on macOS, you can just install Git through that. If you don't use a package management system, then you can download the latest executable installer from the official website and deploy it on your computer. On Linux, installing and using Git is pretty straightforward. You can install it with the command apt install git or yum install git, and after that, you'll have Git installed and ready to use. On macOS, you can even have it installed when you run git ---- version. If Git isn't installed, this command will ask you if you want to install it and then download it and install it for you. Alternatively, you can also download it from the website and install it by following the prompts. Once it's installed, you'll be able to use it from the command line just like any other tool. On Windows, after downloading and executing the installer, you'll need to go through a bunch of different configuration options. These options come with pre-selected defaults that usually make sense to just keep. Pay attention to the editor question though. You'll probably want to change the editor to one that you feel comfortable with, like Notepad++ or Atom. One interesting thing about the Windows installation is that it comes preloaded with an environment called min-gw64. This environment lets us operate on Windows with the same commands and tools available on Linux. So you can practice some Linux command line tools on your Windows machine. After installing Git on your Windows machine, you'll be able to use Git from the Linux command line. And if you selected the default option for the path environment question, you'll be able to also run it from the PowerShell command line. If you want to understand more about each option involved in the installation on Windows, check out the optional video where we'll talk about the available options and when you might want to select something different from the default. Throughout this course, we'll talk about how to do things from the command line. Some integrated developer environments, or IDEs, let us interact with Git through graphical interfaces, and it's fine to use those if you feel more comfortable with them. We'll focus on the command line because it's standard, and also because once you've mastered the command line, you'll definitely be able to use any graphical tool out there. In the next video, we'll look into the options you can set when installing Git on a Windows machine. This video is optional. If you've already set up Git on your computer, you can jump ahead to the next video. In this video, we'll show you how you can install Git on Windows. We'll dive into the different options that you can select and what they all mean. We'll start by downloading the latest version of the software from the gitforwindows.org website. The software package we get includes a bunch of other tools that might come in real handy. It comes with a bash emulation environment, where we can run all the Git commands we'll explain in this course, and a bunch of Unix-like utilities that we'll show in this and other courses. This bundle also includes a graphical user interface to interact with Git. We won't look at it during this course, but you can experiment with it on your own. Alright, we've downloaded the file. Let's get it installed. First, let's start by clicking Keep. The first window we get is the license of the software. Git is released under the GPL version 2 license, which is a free software license. This means that if we want, we can look at Git's code to learn how it works, and we can even modify it to do something different. Alright, let's accept this license and continue with the setup. The first option we get is the installation path. We'll keep it as is. This window lets us select additional components to add to our Git installation. By default, Git integrates with the Windows Explorer to let us run Git command line or the Git graphical interface in the current folder. This software bundle comes with an extension for improving the support of how large files, like audio or video files, get stored in the version control system. It's a good idea to keep this enabled. The installer will also register the Git configuration files as files that should be opened with a text editor, and the .sh files as files that should be executed with bash. All of this makes sense, so we'll keep these options selected. If you want, you can also enable some of the other options. That will cause the icons to be displayed on the desktop, true type fonts to be used in the console, or software to automatically check for updates. Alright, let's keep going. We get prompted for the name of the folder where we want to create all the shortcuts. Git is fine as the name for this, so let's continue. Okay, now's the time to choose the editor. This is the option that you'll most likely want to adjust. You want to select an editor that you're comfortable with. The installer already has a list of possible options that you could choose here, like Notepad++, Visual Studio Code, or Sublime Text. And we could even select any other editor we wanted by entering the path to the editor's executable file. For this course, we'll be using Atom in all of our examples, so let's choose Atom for this installation. Heads up, the bundle doesn't ship with any of these graphical editors installed. You'll need to install the one you want separately. All right, we're now asked to choose how we want to adjust the path environment. This option lets us decide how we want to execute Git from the command line. Selecting the first option will make Git only accessible through the embedded command line that is shipped with the bundle. The second option, the one that's pre-selected, allows us to execute Git from the embedded command line and from the Windows command prompt. The third option will add the Unix-like tools shipped together with Git to the Windows command prompt. If you choose this option, any commands that have the same name as those in the OS will then come from the bundle and not the basic OS. We'll keep the second option selected, as it's the one that's most convenient for us while not interfering with the local tools. This window lets us choose how we want to validate the SSL certificates used for HTTPS connections. We can choose to use the open SSL library that's shipped together with Git, or use the native Windows library. You'll want this second option if you need to interact with your company's internal systems. As we'll only be interacting with GitHub, we'll keep the default option selected. This window lets us select what we want to do about line endings. The characters used to indicate the end of the line are different between Windows, Linux, and macOS. So the Git software bundle lets us decide how we want to handle these differences. The default is to store Windows line endings on the local files, but use Unix line endings in the files stored by Git. This works well when you're using your Windows computer to collaborate with others using a different OS. The second option is to keep the line endings unchanged when copying the files locally, and use Unix line endings for the files stored in Git. This would work well if you're using a Unix-like OS, or if you're only editing through Unix-like editors on Windows. The third option is to not do any conversions. This option doesn't work well if you're trying to work with people using a different OS. So it's only recommended if all your collaborators will be running the same OS as you. All right, let's keep the first one selected and move on. This window lets us configure the terminal emulator. The software bundle ships with its own terminal emulator that includes a bunch of nice features, like better Unicode support and a long history of commands that we can scroll. We'll keep that one selected, but if you feel like you're more comfortable with the Windows default console window, you can choose that one. All right, we have a few extra options that we can choose to enable if we want. We'll keep these as they are. That way, we'll get the performance improvements of letting Git do file system caching. And we'll be able to use Git's credential manager. We don't need to use symbolic links in our repositories, so we'll leave that disabled. Finally, we get one last prompt before installing, which lets us choose which experimental features we want to select. The features offered here will change with time, as some get adopted and others get dropped. You can decide whether you want to work on the bleeding edge, or you'd rather go with what's already well tested. We aren't feeling too adventurous today, so we won't enable the experimental features. We'll just click Install here to get our installation started. All right, Git is installing on our machine. It'll take a while for it to complete. Once it's done, we'll have all the Git goodness at our fingertips. In case you need a bit more help, you can find links for more information regarding Git's installation in our next reading. When starting with Git, There are a bunch of concepts that we need to learn to understand how things are organized and how our files are tracked. Over the next few videos, we'll introduce some of the main Git concepts. If any of these seem confusing at first, don't panic. We'll dive into all of them as we expand our Git knowledge. Let's start by setting some basic configuration. Remember when we said that a VCS tracks who made which changes? For this to work, we need to tell Git who we are. We can do this by using the git config command and then setting the values of user.email and user.name to our email and our name, like this. We use the -- global flag to state that we want to set this value for all Git repositories that we use. We could also set different values for different repositories. With that done, there are two ways to start working with a Git repository. We can create one from scratch using the git init command, or we can use the git clone command to make a copy of a repository that already exists somewhere else. We'll talk about remote repositories later in the course. For now, let's start by creating a new directory and then a Git repository inside that directory. So, when we run git init, we initialize an empty Git repository in the current directory. The message that we get mentions a directory called .git. We can check that this directory exists using the ls-la command, which lists files that start with a dot. We can also use the ls-l.git command to look inside of it and see the many different things it contains. This is called a Git directory. You can think of it as a database for your Git project that stores the changes and the change history. We can see it contains a bunch of different files and directories. We won't touch any of these files directly. We'll always interact with them through Git commands. So whenever you clone a repository, this Git directory is copied to your computer. Whenever you run git init to create a new repository, like we just did, a new Git directory is initialized. The area outside of the Git directory is the working tree. The working tree is the current version of your project. You can think of it like a workbench or a sandbox where you perform all the modification you want to your files. This working tree will contain all the files that are currently tracked by Git and any new files that we haven't yet added to the list of tracked files. Right now, our working tree is empty. Let's change that by copying the disk usage.py file that we saw in an earlier video into our current directory. Okay, we now have a file in our working tree, but it's currently untracked by Git. To make Git track our file, we'll add it to the project using the git add command, passing the file that we want as a parameter. With that, we've added our file to the staging area. The staging area, which is also known as the index, is a file maintained by Git that contains all of the information about what files and changes are going to go into your next commit. We can use the git status command to get some information about the current working tree and pending changes. Let's check that one out. We see that our new file is marked to be committed. This means that our change is currently in the staging area. To get it committed into the Git directory, we run the git commit command. Let's try that now. When we run this command, we tell Git that we want to save our changes. It opens a text editor where we can enter a commit message. If you want, you can change the editor used to your preferred editor. In our case, this computer has Nano configured as the default editor. The text that we get tells us that we need to write a commit message, and that the change to be committed is the new file that we've added. We'll deep dive into commit messages later. For now, let's enter a simple description of what we did, which was to add this one file, and then exit the editor, saving our commit message. And with that, we've created our first Git commit. Woohoo! Up next, we'll talk more about the life cycle of each track file in a Git repository. In our last video, we mentioned that any Git project will consist of three sections: the Git directory, the working tree, and the staging area. The Git directory contains the history of all the files and changes. The working tree contains the current state of the project, including any changes that we've made, and the staging area contains the changes that have been marked to be included in the next commit. This can still be confusing, so it might be helpful to think about Git as representing your project, which is the code and associated files, in a series of snapshots. Each time you make a commit, Git records a new snapshot of the state of your project at that moment. It's a picture of exactly how all these files looked at a certain moment in time. Combined, these snapshots make up the history of your project and its information that gets stored in the Git directory. Now, let's dive into the details of how we track changes to our files. When we operate with Git, our files can be either tracked or untracked. Tracked files are a part of the snapshots, while untracked files aren't a part of snapshots yet. This is the usual case for new files. Each tracked file can be in one of three main states: modified, staged, or committed. Let's look at what each of these mean. If a file is in the modified state, it means that we've made changes to it that we haven't committed yet. The changes could be adding, modifying, or deleting the contents of the file. Git notices anytime we modify our files, but won't store any changes until we add them to the staging area. So, the next step is to stage those changes. When we do this, our modified files become staged files. In other words, the changes to those files are ready to be committed to the project. All files that are staged will be part of the next snapshot we take. And finally, when a file gets committed, the changes made to it are safely stored in a snapshot in the Git directory. This means that typically a file tracked by Git will first be modified when we change it in any way. Then it becomes staged when we mark those changes for tracking. And finally, it will get committed when we store those changes in the VCS. Let's see this in action in our example Git repo. First, let's check the contents of the current working tree using ls-l, and then the current status of our files using the git status command. When we run git status, Git tells us a bunch of things, including that we're on the master branch. We'll learn about branches later in the course. For now, notice how it says that there's nothing to commit and that the working tree is clean. Let's modify our file to change that. For example, we'll just add periods at the end of the message that our script presents to the user. So, now that we've made the change, let's call git status again and see the new output. Again, Git tells us a lot of things, including giving us some tips for commands that we might want to use. These tips can come in real handy, especially when we're familiarizing ourselves with Git. See how the file we changed is now marked as modified, and that it's currently not staged for commit? Let's change that by running the git add command, passing the disk usage py file as a parameter. When we call git add, we're telling Git that we want to add the current changes in that file to the list of changes to be committed. This means that our file is currently part of the staging area, and it will be committed once we run the next git command, git commit. In this case, instead of opening up an editor, let's pass the commit message using the -m flag, stating that we added periods at the end of the sentences. So, we've now committed our stage changes. This creates a new snapshot in the Git directory. The command shows us some stats for the change made. Let's do one last status check. We see that once again, we have no changes to commit, because the change we made has gone through the full cycle of modified, staged, and committed. So to sum up, we work on modified files in our working tree. When they're ready, We stage these files by adding them to the staging area. Finally, we commit the changes sitting in our staging area, which takes a snapshot of those files and stores them in the database that lives in the Git directory. If the way Git works is not totally clear yet, don't worry. It will all sink in with a bit more practice. In our next video, we'll put this all together and go over the typical workflow when working with Git. In earlier videos, we discussed some of the basic concepts involved in working with Git. We saw that each repository will have a Git directory, a working tree, and a staging area. And we called out that files can be in 3 different states: modified, staged, and committed. Let's review these concepts one more time by looking at the normal workflow when operating with Git on a day-to-day basis. First, all the files we want to manage with Git must be a part of a Git repository. We initialize a new repository by running the git init command in any file system directory. For example, let's use the makedir command to create a directory called scripts, and then change into it and initialize an empty Git repository in it. Our shiny new Git repository can now be used to track changes to files inside of it. But before jumping into that, let's check out our current configuration by using the git config-l command. There's a bunch of info in there, and we won't cover all of it. For now, pay special attention to the user.email and the user.name lines, which we touched on briefly in an earlier video. This information will appear in public commit logs if you use a shared repository. For privacy reasons, you might want to use different identities when dealing with your private work and when submitting code to public repositories. We'll include more details about changing this information in our next reading. Okay. Our repo is ready to work, but it's currently empty. Let's create a file in it. We'll start with a basic skeleton for a Python script, which will help us demonstrate the Git workflow. As with any Python script, we'll start with the shebang line. For now, we'll add an empty main function, which we'll fill in later. And at the end, we'll just call this main function. All right, we've created our file. This is a script that we'll want to execute. So let's make it executable, and then let's check the status of our repo using git status command. As we called out before, when we create a new file in a repository, it starts off as untracked. We can make all kinds of changes to the file, but until we tell Git to track it, Git won't do anything with an untracked file. Do you remember what command we have to use to make Git track our file? That's right. We need to call the git add command. This command will immediately move a new file from untracked to staged status. And as we'll see later, it will also change a file in the modified state to staged state. Remember that when a file is staged, it means it's been added to the staging area and it's ready to be committed to the Git repository. To initiate a commit of staged files, we issue the git commit command. When we do this, Git will only commit the changes that have been added to the staging area. Untracked files or modified files that weren't staged will be ignored. Calling git commit with no parameters will launch a text editor. This will open whatever has been set as your default editor. If the default editor is not the one you'd like to use, there are a bunch of ways to change it. We'll include more info about changing the default editor in the next reading. For now, let's edit our message with nano, which is the current default for this computer. We'll say that our change is creating an empty allchecks.py file, then save and exit. Voila! We've just recorded a snapshot of the code in our project, which is stored in the Git directory. Remember that every time we commit changes, we take another snapshot, which is annotated with a commit message that we can review later. Okay, that's how we add new files, but usually we'll modify existing ones. So let's add a bit more content to our script to see that in action. We'll add a function called check reboot that will check if the computer is pending a reboot. To do that, we'll check if the run/reboot-required file exists. This is a file that's created on our computer when some software requires a reboot. And of course, since we're using os.path.exists, we need to add import os to our script. All right, we've added a function to our file. Let's check the current status using git status again. Our file is modified, but not staged. To stage our changes, we need to call git add once again. Okay, our changes are now staged. What do we need to do next? You got it. We have to call git commit to store those changes to the Git directory. This time we'll use the other way of setting the commit message. We'll call git commit-m and then pass the commit message that we want to use. So in this case, we'll say that we've added the check_reboot function. With that, we've demonstrated the basic Git workflow. We make changes to our files, stage them with git add, and commit them with git commit. Are you starting to feel more comfortable with this process and see how it fits within the rest of your tasks? If there's anything that's not totally clear yet, remember that the only way to get familiar with these concepts is practice. Feel free to try these examples out on your computer as we go along until you get comfortable with these commands. Up next, we'll talk more about how to write useful commit messages. In earlier videos, we saw how we can commit snapshots of changes to the Git repository. Let's now talk a little bit more about what makes a good commit message. Writing a clear, informative commit message is important when you use a VCS. Future you or other developers or IT specialists who might read the commit message later on will really appreciate the contextual information as they try and figure out some of the parts of the code or configuration. So what makes a good commit message? It can be helpful to keep your audience in mind when you write commit messages. What would someone reading a message weeks or months from now want to know about the changes you've made? What might be especially important or tricky to understand about them? Is there extra information that might help the reader out, like links to design documents or tickets in your ticketing system? Similar to how style guides exist for writing code, your company might have specific rules for you to follow when you write commit messages. Even if they don't, it's good to use a few general guidelines to make sure your commit messages are as clear and useful as possible. A commit message is generally broken up into a few sections. The first line is a short summary of the commit, followed by a blank line. This is followed by a full description of the changes, which details why they're necessary and anything that might be especially interesting about them or difficult to understand. When you run the git commit command, Git will open up a text editor of your choice so you can write your commit message. A good commit message might look something like this. So the first line is usually kept to about 50 characters or less. The line contains a short description of what the commit changes are about. After the first line comes an empty line, and the rest of the text is usually kept under 72 characters. This text is intended to provide a detailed explanation of what's going on with the change. It can reference bugs or issues that will be fixed with the change. It can also include links to more information when relevant. The line limits can be annoying, but they help in making the commit message be more digestible for the reader. There's a git command used to display these commit messages called git log. This command won't do any line wrapping for us, which means that if we don't stick to the recommended line wrapping, long commit messages will run off the edge of the screen and be difficult to read. Now, take a look at the lines in the commit message that start with the pound symbol. Just like in Python, this symbol indicates that these lines are comments and won't get included in the commit message. Git shows them to us whenever we're writing a commit message, as a reminder of what files we're about to commit. Sometimes it can be tempting to just write something short like update, change, or fix as the description of our commit messages. Don't do it. It's super frustrating to go back to a repository's history and discover that there's not enough context to understand what was changed and why. It takes only a few more seconds to write a better description. This can be invaluable down the line. Following these guidelines can help make your commit messages really useful, and the investment of work now will really pay off later. If you're interested in learning more about Git commit style, there are plenty of resources out there to read, including the Linux kernel documentation itself, along with impassioned opinions from other developers. We'll include links to all of them in the next reading. We said that we can check the history of the commits of our project using the git log command. Let's go back to our example scripts directory where we've performed 2 commits and check out what git log has to say about those 2 commits. Take a look at what Git tracks as part of the log. It's packing a lot of information in just a few lines. The first thing listed for each commit is its identifier, which is a long string of letters and numbers that uniquely identify each commit. The first commit in the list also says that the head indicator is pointing to the master branch. If this is gibberish to you, don't worry. We'll talk more about what head and master means in later videos. For each commit, we see the name and the email of the person who made the commit, which is indicated as the author. Then we get the date and time the commit was made. Finally, the commit message is displayed. Our commit messages are very brief, as we're just starting to work on our repository. As the work we do becomes more complex, we'll probably write longer descriptions with a lot more detail. Coming up, we've got a cheat sheet for you that lists all the Git commands we've seen up until now, along with links to additional information that you might find useful. After that, head over to the next practice quiz to help make sure you've wrapped your head around all these new concepts. Congrats! You made it to the end of the module. These aren't easy concepts, seriously, and I'm thrilled that you made it this far. Over the past videos, we looked into what version control is and why we even need it. We discussed how version control systems can enable collaboration across thousands of people, and also how it can be a great tool for people working on their own or in very small teams. We then jumped into Git. We've discussed the basic Git concepts and looked at the typical Git workflow. By now, you've taken your first steps with Git. The workflow we've looked at so far is very simple, but it's already useful for helping you keep track of your changes. As you expand your Git knowledge, you'll discover many more things you'll be able to do with it. We've said this before, and we'll no doubt say it again, the best way to learn anything worth knowing is through practice. Practice and more practice. That's why you're going to practice all this new knowledge by following the Git workflow on your own for the graded assessment. For the graded assessments in this course, we'll use the QuickLabs online learning platform, which is powered by the Google Cloud Console. This platform lets you experience real-world scenarios where you're the one in charge of getting things done. To interact with the labs, you have to connect to virtual machines running in the cloud. Each lab will present a different activity to be done with Git, and you'll get the chance to practice your new skills. The exercise that you'll need to do for this assessment will be very similar to the examples we've covered here. You'll have to initialize a repository, add content to it, and then commit that content so that it can be tracked. It's not magic, but getting comfortable with this process will prove really valuable in the upcoming modules. So now's the time to commit to reviewing all the examples and getting these new concepts committed to memory. And me? I'm committing to seeing you in the next module. Catch you there. Welcome back. Up till now, we've talked about what version control is, why it's necessary, and how we might benefit from it in diverse contexts. We also started learning some basic Git commands and procedures. Nice job! Over the course of the next videos, we'll go into much more detail about what we can do with Git. These are Git's greatest hits. We'll start by learning some handy shortcuts and looking into how we can get more info out of our version control system. Then, we'll experience the true power of Git by seeing how we can undo some of our changes. The ability to revert previous changes is one of the most useful aspects of version control systems. Depending on what needs to be undone, there's a bunch of different techniques that we can use in Git. We can discard the changes made to a file, fix a commit that was incorrect, and even roll back our project to an older snapshot. We'll look into all these techniques and dive into when to use each of them. Finally, we'll check out yet another important concept: branches. We can use branches to work on an experimental feature without affecting the main code of our project. Support separate versions of a program that can't be merged together, and much more. We'll dive into what branches are, when and how to use them, and how to deal with merge conflicts. Admittedly, some of these concepts can get pretty tricky. So we really recommend that you follow along on your computer, experiment with the commands that we show, and try things on your own until you feel comfortable with these techniques. Remember that you can always go back and review any earlier videos if something isn't totally clear. So are you ready to learn more about advanced features in Git? Let's get to it. When we covered the basic Git workflow, we called out that the process is usually to make changes, stage them, and then commit them. The separate step between staging and committing allows us to stage several changes in one commit. But if we already know that the current changes are the ones that we want to commit, we can skip the staging step and go directly to the commit. No dress rehearsals. We do this by using the -a flag to the git commit command. This flag automatically stages every file that's tracked and modified before doing the commit, letting us skip the git add step. At first, you might think that git commit -a is just a shortcut for git add followed by git commit, but that's not exactly true. Git commit -a doesn't work on new files because those are untracked. Instead, git commit -a is a shortcut to stage any changes to tracked files and commit them in one step. If the modified file has never been committed to the repo, we'll still need to use git add to track it first. So, let's make a change to our example script from an earlier video and try out this new flag. We'll now modify our main function and make it call the check reboot function that we wrote before. If a reboot is pending, we'll print a message and then exit our program with an exit status of 1. And since we're using the sys module, we'll need to import it. All right, now that we've made the change, we're ready to try out the new -a flag. We'll also use the -m flag to add the commit message directly. This time, we'll say that we're calling check_reboot and exiting with 1 on the error condition. Success! These shortcuts are useful when making small changes that we know we'll want to commit directly without keeping them in the staging area and having to write long and complex descriptions. Keep in mind that when you use the -m shortcut, you can only write short messages and can't use the best practices regarding commit descriptions that we talked about earlier. So, it's best reserved for truly small changes that don't require extra context or explanation. Short and sweet. Heads up, when you use the -a shortcut, you skip the staging area, meaning you can't add any other changes before creating the commit. So you need to be sure that you've already included everything you want to include in that commit. In the end, using a shortcut like -a is just like using the regular commit workflow. The commit will show up in the log along with the message just as usual. Let's check that out. See how our latest commit was added to the top of the list of commits? And notice how the head indicator has now moved to the latest commit? You might be wondering, what is this head and where is it heading? We'll keep coming across it, so let's clarify. Git uses the head alias to represent the currently checked out snapshot of your project. This lets you know what the contents of your working directory should be. In this case, the current snapshot is the latest commit in the project. We'll soon learn about branches, and in that case, head can be a commit in a different branch of the project. We could even use Git to go back in time and have head represent an old commit from before the latest changes were applied. In all cases, head is used to indicate what the currently checked out snapshot is. This is how Git marks your place in the project. Think about it as a bookmark that you can use to keep track of where you are. Even if you have multiple books to read, the bookmark allows you to pick up right where you left off. When you run Git commands like diff, branch, or status, Git will use the head bookmark as a basis for whatever operation it's performing. We'll see head used when we learn how to undo things and perform rollbacks, and we'll talk more about branches in later videos. As a shortcut, it's generally easy to think of head as a pointer to the current branch, although it can be more powerful than that. Up next, we'll dig into how we can get more information about our changes both before and after we commit them. We've seen how Git log shows us the list of commits made in the current Git repository. By default, it prints the commit message, the author, and the date of the change. This is useful, but if we're combing through a history of changes in a repo to try and find what caused the latest outage, we'll probably also need to look at the actual lines that changed in each commit. To do this with Git log, we can use the -p flag. The P comes from patch, because using this flag gives us the patch that was created. Let's try it out. The format is equivalent to the diff-u output that we saw in an earlier video. It shows added lines with pluses and removed lines with dashes. Because the amount of text is now longer than what fits on your screen, Git automatically uses a paging tool that allows us to scroll using page up, page down, and the arrow keys. We still have one commit below the other, but now each commit takes up a different amount of space, depending on how many lines were added or removed in that commit. Using this option, we can quickly see what changes were made to the files in our repository. This can be especially useful if we're trying to track down a change that recently broke our tools. If we don't want to scroll down until we find the commit that we're actually interested in, another option is to use the git show command. This command takes a commit ID as a parameter and will display the information about the commit and the associated patch. We'll talk more about commit IDs in a later video, but for now, remember that this is an identifier that we see next to the word commit in the log. Let's check this out by first listing the current commits in the repo and then calling git show for the second commit in the list. First, I'm going to exit out by pressing Q. We've shown how we can use git log for listing commits and git log-p for showing the associated patches. Another interesting flag for git log is the --stat flag. This will cause git log to show some stats about the changes in the commit, like which files were changed and how many lines were added or removed. Let's try it with our repo. There are a bunch of other options to git log, so we won't cover them all. You can always use the reference documentation or the manual pages to find out more. And, as we called out before, you don't need to memorize any of this. You'll learn the different commands and flags by using them. The important thing to remember is that all the information is stored in the repository and you have it at your fingertips when you need it. You're welcome. Now, what about changes that haven't been committed yet? Until now, whenever we've made changes to our files, we've either added them to the staging area with git add and committed them with git commit, or committed them directly using git commit-a. This works fine, but it means we have to know exactly which changes we've made. Sometimes it can take a while until we're ready to commit. We call these commitment issues. Just kidding. But imagine you've been working on adding a new complex feature to a script and it requires thorough testing. Before committing it, you need to make sure that it works correctly. Check that all the test cases are covered, and so on and so on. So while doing this, you find bugs in your code that you need to fix. It's only natural that by the time you get to the commit step, you don't really remember everything you've changed. To help us keep track, Git gives us the git diff command. Let's make a new change to our script and then try this command out. We'll add another message to the user to say that everything is okay when the check is successful, and then exit with 0 instead of 1. Okay, we've made the change. Let's now save it and check out what git diff shows us. Again, this format is equivalent to the diff-u output that we saw in an earlier video. In this case, we see that the only change is the extra lines that we've added. If our change was bigger and included several files, we could pass a file by parameter to see the differences relevant to that specific file, instead of all the files at the same time. Something else we can do to review changes before adding them is to use the -p flag with the git add command. When we use this flag, Git will show us the change being added and ask us if we want to stage it or not. This way, we can detect if there's any changes that we don't want to commit. Let's try that one out. We've staged our change and it's now ready to be committed. If we call git diff again, it won't show any differences, since git diff shows only unstaged changes by default. Instead, we can call git diff -- staged to see the changes that are staged but not committed. With this command, we can see the actual staged changes before we call git commit. Let's commit these changes now so that they aren't pending anymore. We'll say that we've added a message when everything is okay. Nice. And with that, we've learned a bunch of different ways to get more information about our changes. We've covered a lot of ground, so take the time to review and practice these commands if they don't make sense yet. Up next, we'll look into what happens when we want to delete or rename files in our repository. It's time to do a little housekeeping. Let's say that you've decided to clean up some old scripts and want to remove them from your repository. Or you've done some refactoring, which makes a particular file obsolete. You can remove files from your repository with the git rm command, which will stop the file from being tracked by Git and remove it from the Git directory. File removals go through the same general workflow that we've seen, so you'll need to write a commit message as to why you've deleted them. Let's try this out in our checks repository that contains a file we decided we actually don't want. We'll first look at the contents of the directory with ls, then delete the file with git rm, then check the contents with ls again, and finally check the status with git status. So, we see that by calling git rm, the file was deleted from the directory and the change was also staged to be committed in our next commit. Let's do that now by calling git commit and setting a message indicating that we've deleted the unneeded file. As usual, we get a bunch of stats when we do the commit. Check out all the deletions it reported. These are all lines in the file that are no longer there, and it states that the file itself was deleted. What if you have a file that isn't accurately named? This can happen. For example, if you start writing a script that you thought would only do one thing and then expands to cover more use cases, or conversely, if you named your script thinking that it would be very generic, but it ends up being more specific. You can use the git mv command to rename files in the repository. Let's rename our existing script to checkfreespace.py and then check what git status has to say about that. The status shows us that the file was renamed and clearly displays the old and new names. As with the previous example, the change is staged but not committed. Let's commit it by calling git commit once again. The git mv command works in a similar way to the mv command on Linux, and so can be used for both moving and renaming. If our repository included more directories in it, we could use the same git mv command to move files between directories. As you can probably tell from our examples, the output of git status is a super useful tool to help us know what's up with our files. It shows us which files have tracked or untracked changes, and which files were added, modified, deleted, or renamed. It's important that the output of these commands stays relevant to what we're doing. If we have a long list of untracked files, we might lose an important change in the noise. If there are files that get automatically generated by our scripts, or our operating system generates artifacts that we don't want in our repo, we'll want to ignore them so that they don't add noise to the output of git status. To do this, we can use the git ignore file. Inside this file, we'll specify rules to tell Git which files to skip for the current repo. For example, if we're working on an OS X computer, we'll probably want to ignore the .dsstore file, which is automatically generated by the operating system. To do this, we'll create a .gitignore file containing the name of this file. Remember that the dot prefix in a Unix-like file system indicates that the file or directory is hidden and won't show up when you do the normal directory listing. That's why we have to use ls-la to see all files. We've added a git ignore file to our repo, but we haven't committed it yet. This file needs to get tracked just like the rest of the files in the repo. Let's add it now. Looks great. We've learned a lot of new commands and techniques related to Git in these past videos. Coming up, we've put together a cheat sheet listing all the new commands and options. After that, a quiz to let you practice these concepts. Now go on, Git. Being able to revert our changes is one of the most powerful features offered by version control systems. And there's a bunch of different techniques available depending on which changes we need to undo. In this video and the next few coming up, we'll talk about the most common ways to revert changes in Git and when to use each approach. For example, you might find yourself in a situation where you've made a bunch of changes to a file, but decide that you don't want to keep them. You can change a file back to its earlier committed state by using the git checkout command, followed by the name of the file you want to revert. Speaking of, let's try this out using our scripts repository. We'll edit our allchecks.py script and remove the check reboot function, then save and go back to the command line. Cool, we've made our change. Let's try our script and see what happens. Oof, by deleting that function, we've actually broke the script. Let's see what git status has to say about this. As expected, we see that our file is modified and the changes aren't staged yet. Check out how Git gives us a couple helpful tips on what to do now. We can run git add to stage our changes, or we can run git checkout to discard them. If you need help remembering what this command does, think of it this way. You're checking out the original file from the latest stored snapshot. Let's do that now. We'll check out at the original file and then take a look at what git status has to say about it, and finally retry our script. Oops, looks like we have a typo. Let's go back and fix it. Done and done. With that, we've demonstrated how we can use git checkout to revert changes to modified files before they get staged. This command will restore the file to the latest stored snapshot, which can be either committed or staged. So, if you've made additional changes to a file after you've staged it, you can restore the file to the earlier staged version. And if you need to check out individual changes instead of the whole file, you can do that using the -p flag. This will ask you change by change if you want to go back to the previous snapshot or not. Okay, that's it for undoing unstaged changes. But what if you added the changes to the staging area already? Don't stress. If we realize we've added something to the staging area that we didn't actually want to commit, we can unstage our changes by using the git reset command. Staging changes that we don't actually intend to commit happens all the time, especially if we use a command like git add star, where the star is a file glob pattern used in bash that expands to all files. This command will end up adding any change done in the working tree to the staging area. And while sometimes that might be what we want, it can also lead to some surprises. Let's try it out with an example. First, we'll pretend we're trying to debug a problem in our script. And for that, we create a temporary file with the output of our script. Then, we'll add all unstaged changes in our working tree using git add star. And finally, check the status using git status. We can see that this output file, which was supposed to be a temporary file for debugging, has now been staged in our repo, but we didn't want to commit it. Conveniently, the git status command tells us how to unstage the file right there in the output. The example output mentions the head alias. Remember what that means? That's right. It's the current checked out snapshot. So, by running the suggested command, we're resetting our changes to whatever's in the current snapshot. Let's try it out. Ta-da! The file is once again untracked in our working tree and no longer staged. You can think of reset as the counterpart to add. With add, you can, well, add changes to the staging area. With reset, you remove changes from the staging area. And you can use git reset-p to get Git to ask you which specific changes you want to reset. Get it? But wait, let's remember to commit our typo fix. With that, we've seen how we can revert unstaged and staged changes. But what if you've already created a commit with the changes that you want to undo? Great question. That's coming up in the next video. In general, we try to make sure our commits include all the right changes and descriptions. But we're all human, and we make mistakes. It's not uncommon for developers and IT specialists to realize that there is an error in a recent commit, which is why it's important to know how to take action and fix it. Let's say you just finished committing your latest batch of work, but you've forgotten to add a file that belongs to the same change. You'll want to update the commit to include that change. Or maybe the files were correct, but you realize that your commit message just wasn't descriptive enough. So you want to fix the description to add a link to the bug that you were solving with that commit. What can you do? We can solve problems like these using the -- amend option of the git commit command. When we run git commit -- amend, Git will take whatever is currently in our staging area and run the git commit workflow to overwrite the previous commit. Let's see this in an example. We'll go to our scripts directory and create 2 new files using the touch command. Then list the content of the directory using ls, add our Python script, and commit it saying that we've added 2 files. As you can see, the message printed by Git says that only 1 file was added. Our commit message said that we added 2 files, but we forgot to add one of them. Ouch. Don't panic, we can fix it. We'll start by adding the missing file and then amending our commit. We called git commit -- amend, and an editor opened up showing the commit message and the stats about the commit that we're working with. The list of added files for this commit now includes both files that we wanted to add. Yay! Now that the files have been added, we can also improve our initial commit message, which was a bit too short. We'll keep the existing description as the first sentence of our commit, and then add a line of description about the intended purpose of each file. Okay, with that, our commit is ready to be amended. Let's save the new description as usual. Woohoo! We've amended our previous commit to include both files and a better message. You could also just update the message of the previous commit by running the git commit -- amend command with no changes in the staging area. An important heads up, while git -- amend is okay for fixing up local commits, you shouldn't use it on public commits, meaning those that have been pushed to a public or shared repository. This is because using -- amend rewrites the Git history, removing the previous commit and replacing it with the amended one. This can lead to some confusing situations when working with other people and should definitely be avoided. So remember, fixing up a local commit with amend is great, and you can push it to a shared repository after you fixed it, but you should avoid amending commits that have already been made public. If this sounds confusing now, don't worry. We'll mention it again when we talk about collaborating with others through shared repositories. Okay, we've covered how to fix staged and unstaged changes, and how to fix a commit that was incomplete. Up next, we'll talk about what to do if you come across a bad commit that needs to be completely reverted. Fixing your work before you commit is good, but what happens if it's already been snapshotted by Git? Let's say you host a Git repository on a company server that contains all kinds of useful automation scripts that you and your coworkers use. One morning before coffee, you make a few changes to one of these scripts and commit the updated files. A few hours later, you start to receive tickets from users indicating some part of the script is broken. From the errors they describe, it sounds like the problem is related to your recent changes. Uh-oh. You could look at the code you updated to see if you can spot the bug, but more tickets are pouring in and you want to fix the problem as fast as possible. You've decided it's time for a rollback. There are a few ways to roll back commits in Git. For now, we'll focus on using the git revert command. In Git, revert doesn't just mean undo. Instead, it creates a commit that contains the inverse of all the changes made in the bad commit in order to cancel them out. For example, if a particular line was added in the bad commit, then in the reverted commit, the same line will be deleted. This way, you get the effect of having undone the changes, but the history of the commits in the project remains consistent, leaving a record of exactly what happened. So, git revert will create a new commit that is the opposite of everything in the given commit. We can revert the latest commit by using the head alias that we mentioned before. Since we can think of head as a pointer to the snapshot of your current commit, when we pass head to the revert command, we tell Git to rewind that current commit. Make sense? To check this out, we'll first add a faulty commit to our example repo. Okay, we've added some code to our script. Let's save and commit this. So now our code is committed. We didn't even test it, which is a bad idea if you're doing this for real. And you might have already spotted the problem with our code. This is where our users start filing tickets and saying that things are broken. And so we run our script to see what happens. Oops. We used a function that we forgot to define. Okay, it's rollback time. Let's get rid of this faulty code by typing git revert head. So, once we issue the git revert command, we're presented with the text editor commit interface that we've all seen before. In this case, we can see that Git has automatically added some text to the commit, indicating it's a rollback. The first line mentions that it's reverting the commit we just did called add call to disk full function. The extra description even includes the identifier of the commit that got reverted. While we could use this description as is, it's usually a good idea to add an explanation of why we're doing the rollback. Remember that the goal of these descriptions is to help our future selves understand why things happened. In this case, we'll explain that the reason for the rollback is that the code was calling a function that wasn't defined. Once we're done entering the description, we can exit and save as usual. You'll notice the output that we get from the git revert command looks like the output of the git commit command. This is because git revert creates a commit for us. And since a revert is a normal commit, we can see both the commit and the reverted commit in the log. Let's look at the last two entries in the log using -p and -2 as parameters. As demonstrated before, the -p parameter lets us see the patch created by the commit, while the -2 parameter limits the output to the last two entries. So, in this log, we can see that when we called revert, Git created a new commit that's the inverse of the previous one. This removes the lines that we added in the previous commit. We can see that the original commit shows the lines we added by preceding them with a plus sign. The same line shows up with a minus sign in the newer commit message, indicating that they were removed. Just like that, the bad commit is reverted and the errors stop. Phew! In this example, we reverted the latest commit in our tree. But what if we had to revert a commit that was done before that? Rev up your time machines, because in the next video, we're turning back the clock big time. So far, we've used the head alias to specify the most recently checked out commit in our Git history. In our bad snapshot example, the error also happened to be in the most recently created commit, but errors can sometimes take a while to be detected. And so we might need to revert other commits farther back in time. We can target a specific commit by using its commit ID. We've seen commit IDs a few times already. They show up when we're running the git log command, and we also saw the commit ID of the reverted commit in our last example. Commit IDs are those complicated looking strings that appear after the word commit in the log messages. Let's have a look at the latest log entry in our checks repo. The commit ID is the 40-character long string after the word commit. You really can't miss it. This long jumble of letters and numbers is actually something called a hash, which is calculated using an algorithm called SHA-1. Essentially, what this algorithm does is take a bunch of data as input and produce a 40-character string from the data as the output. In the case of Git, the input is all information related to the commit, and the 40-character string is the commit ID. Cryptographic algorithms like SHA-1 can be really complex, so we won't go too deep into what this means. If you're interested, you'll find links to more information in the next reading. Still, you might be wondering, why on earth would you use a long jumble of letters as an ID for a commit, instead of incrementing an integer like 1, 2, 3, etc.? To answer that, let's take a quick look at the reason why Git uses a hash instead of a counter, and how that hash is computed. Although SHA-1 is a part of the class of cryptographic hash functions, Git doesn't really use these hashes for security. Instead, they're used to guarantee the consistency of our repository. Having consistent data means that we get exactly what we expect. To quote Git's creator, Linus Torvalds, you can verify the data you get back out is the exact same data you put in. This is really useful in distributed systems like Git, because everyone has their own repository and is transmitting their own pieces of data. Computing the hash keeps data consistent because it's calculated from all the information that makes up a commit: the commit message, date, author, and the snapshot taken of the working tree. The chance of two different commits producing the same hash, commonly referred to as a collision, is extremely small. So small, it wouldn't happen by chance. It'd take a lot of processing power to cause this to happen on purpose. If you use a hash to guarantee consistency, you can't change anything in the Git commit without the SHA-1 hash changing too. Remember our discussion about fixing commits with the -- amend command? Each time we amend a commit, the commit ID will change. This is why it's important not to use -- amend on commits that have been made public. The data integrity offered by the commit ID means that if a bad disk or network link corrupts some data in your repository, or worse, if someone intentionally corrupts some data, Git can use the hash to spot that corruption. Aha, it will say, the data you've got isn't the data you expected. Something went wrong. Thank you, Detective Git. You've saved the day once again. Okay, enough backstory. How can you use commit IDs to specify a particular commit to work with, like during a rollback? Let's look at the last two entries in our repo using the git log -2 command. Say we realize that we actually like the previous name of our script, and so we want to revert this commit where we renamed it. First, let's look at that specific commit using git show, which we mentioned in an earlier video. We've copied and pasted the commit ID that we wanted to display, and that works. Alternatively, we could provide just the first few characters identifying the commit to the command, and Git will be smart enough to guess which commit ID starts with those characters, as long as there's only one matching possibility. Let's try this out. Two characters is not enough, but usually 4 to 8 characters will be plenty. Okay, now that we've seen how we can identify the commit that we want to revert, let's call the git revert command with this identifier. As usual, this will open an editor where we should add a reason for the rollback. In this case, we'll say that the previous name was actually better. Hooray for flip-flopping! As we called out before, when we generate the rollback, Git automatically includes the ID of the commit that we're reverting. This is useful when looking at a repo with a complicated history that includes a lot of commits. Now, once we save and exit the commit message, Git will actually perform the rollback and generate a new commit with its own ID. See how before the name of our commit, the revert command already shows the first 8 characters of the commit ID? Let's use git show to look at it. All right, we've managed to revert a commit that wasn't the most recent one. Well done, time travelers. Over the past several videos, we've covered a bunch of ways to undo things in Git, whether for unstaged changes, staged changes, amending commits, or rolling back changes. If anything still seems unclear, now's a great time to practice these commands on your local computer, try things out, and come up with more examples of use cases you want to test. Up next, we've spun up a handy cheat sheet summarizing all the content we just covered. When you're ready, move on to the next quiz and put all this new knowledge into practice. We've been learning a lot of complex things over the past few videos, so once you're done with that quiz, you should reward yourself for getting through this technical detail with a break. You earned it. Grab a coffee, tea, or snack and let the concepts settle for a bit. I'll meet you over the next video. Up until now, we've only briefly mentioned branches. You might have seen the text on branch master in commit messages, or you might remember that we talked about branches in the context of the head pointer. Branches are an important part of the Git workflow, so we'll branch out and explore them more thoroughly in the coming videos. So what is a branch, and what is it used for? In Git, a branch at the most basic level is just a pointer to a particular commit. But more importantly, it represents an independent line of development in a project, of which the commit it points to is the latest link in a chain of development history. The default branch that Git creates for you when a new repository is initialized is called master. All of our examples and development have taken place on this branch so far. The master branch is commonly used to represent the known good state of a project. When you want to develop a feature or try something new in your project, you can create a separate branch to do your work without worrying about messing up this current working state. If this seems confusing, maybe an analogy will help. You can think of a Git project as an assignment your teacher gives you in a class. You do all your work on the assignment in a set of notebooks, each notebook representing a different branch. You use some notebooks to jot down rough drafts and experiments, but you keep one notebook, the master branch, in a tidy state, and you copy the polished versions of these drafts into it. No doodling in the master notebook, please. Branches make it really easy to experiment with new ideas or strategies in projects. When you want to add a feature or fix something, you can create a new branch and do your development there. You can merge back into the master branch when you've got something you like, or discard your changes without negative impact if they don't work out. In Git, branches are used all the time as a part of the normal development workflow. As an example, think back to the problematic commit we fixed in an earlier video. We added a call to the disk full function, but forgot to actually define the function. So we had to roll it back because our users were seeing errors. Knowing what we know now, we could have done that work on a separate branch, maybe called something like add disk full. In that case, we could have iterated on our code there until it was working correctly without it affecting the master branch. Only after the code was ready to be deployed, we would merge those changes back into the master branch. In the next few videos, we'll look into how to create new branches and merge their content into the master branch. We'll also go over what to do if you run into any scary merge conflicts. Heads up, this is about to get pretty complicated. So make sure that you follow all of our exercises along on your computer. And keep practicing coming up with new ways of using branches and merging until you're comfortable with each of the steps we show. As branches are essential to how work is done in Git, there's tons of different ways to work with them. We can use the git branch command to list, create, delete, and manipulate branches. Running git branch by itself will show you a list of all the branches in your repository. Let's try it out in our checks repo. Our list is looking pretty empty right now. But don't worry, creating a branch is a snap. We do it by calling git branch with the name of the new branch. Let's create a new feature branch and then list the branches again with git branch. Our new branch was created based on the value of head. Remember that this might not necessarily be the master branch. The list we get shows that we're still on the master branch. We can tell because the current branch is indicated in the command's output with an asterisk in a different color. We'll look into other things that git branch lets us do with branches later on, but right now we want to switch to a new branch. To do that, we'll need to use the git checkout command. We saw earlier how we can use git checkout to restore a modified file back to the latest commit. Checking out branches is similar in that the working tree is updated to match the selected branch, including both the files and the Git history. If this seems a bit confusing at first, you are not alone. I also found it hard to wrap my head around at first, but rest assured that it will become clearer after we use these commands for a while. It might help to remember that we use git checkout to check out the latest snapshot for both files and for branches. All right. Let's switch to our new feature branch by calling git checkout new feature and then listing our branches once again. Before, we were working on the master branch, but now that we've changed to our new branch, the star has moved to new feature. Creating a branch and switching to it immediately is a pretty common task. So common that Git gives us a useful shortcut to create a new branch and to switch to it in a single command. We can use the git checkout-b new branch to do this. Take a look. See how the message says that we've switched to a new branch? Git created the new branch and switched to it in just one command. Super efficient, right? All right, now that we have our shiny new branch, let's create a new file in it. We'll create a new Python 3 file that will include the usual shebang line, an empty main function, and a call to that function. This file is empty because it's only the beginning of our work. As it's in a separate branch, it's okay for it to not be finished yet. Let's save our file and commit it to the current branch now. All right, we've added a commit in this branch and it's looking better. Let's check the last two entries in the log. We see the last two commits in this branch. Notice how next to the latest commit ID, Git shows that this is where head is pointing to, and that the branch is called even better feature. And next to the previous commit, Git shows that both the master and the new feature branches are pointing to that snapshot of the project. In this way, we can see that the even better feature branch is ahead of the master branch. With that, we've seen how we can create new branches and commit changes to them. You might say your knowledge of branches has grown. Up next, we'll learn even more things we can do to operate with branches. So stick around. In our last video, we created a new branch different than the master branch and added a commit to it. Let's check out the current status of our repo by calling git status and ls-l. So, we see that we're on a clean working tree in the even better feature branch, and that the new free memory py file is in our working tree. Let's now change back to the master branch using git checkout master and then list the latest 2 commits there. When we switch to a different branch using git checkout, under the hood, Git changes where head is pointing. Thanks to this checkout, head went from pointing to the latest commit in the even better feature branch to the most recent commit of the master branch. The commit from even better feature doesn't show up at all, and the latest snapshot is the second entry we've seen before. Remember that when we switch branches, Git will also change files in our working directory or working tree to whatever snapshot head is currently pointing at. Let's look at the current contents of our directory. Whoa. Free memory py isn't there. This demonstrates that when we switch branches in Git, the working directory and commit history will be changed to reflect the snapshot of our project in that branch. When we check out a new branch and commit on it, those changes will be added to the history of that branch. Since free memory py was committed on another branch, it doesn't show up in the history or working directory of the master branch. One thing to note after all this back and forth is that each branch is just a pointer to a specific commit in a series of snapshots. It's very easy to create new branches because there isn't any data that needs to be copied around. When we switch to another branch, we check out a different commit and Git updates both head and the contents of our working directory. Head floats around with us. It's like a free spirit. What a head trip. Okay, we've now seen how to create and switch between branches. So what if we want to delete a branch that we don't need anymore? We can do that by using git branch -d. Let's first list the current branches in our repo, and then get rid of the new feature branch by calling git branch -d new feature. And just like that, our branch was trimmed. We can check with another call to git branch that is not there anymore. If there are changes in the branch we want to delete that haven't been merged back into the master branch, Git will let us know with an error. Helpfully, Git also gives us the command to run if we were sure that we wanted to delete the branch, even if it has unmerged changes. But we won't do that just yet. We actually want to merge those changes back into the repo first. And how do we do that? It's all coming up in our next video. A typical workflow for managing branches in Git is to create a separate branch for developing any new features or changes. Once the new feature is in good shape, we merge the separate branch back into the main trunk of code. Merging is the term that Git uses for combining branch data and history together. We'll use the git merge command, which lets us take the independent snapshots and history of one Git branch and tangle them into another. Let's try this out with our example branch from the last video. First, we'll check that we're in the master branch, and then we'll call git merge even better feature to merge the even better feature branch into the master branch. Now we've brought the master branch up to speed, which we can see by looking at the Git log. As we're on the master branch, head points at master. We can see the even better feature and master branches are now both pointing at the same commit. Git uses 2 different algorithms to perform a merge: fast forward and 3-way merge. The merge we just performed is an example of a fast forward merge. This kind of merge occurs when all the commits in the checked out branch are also in the branch that's being merged. If this is the case, we can say that the commit history of both branches doesn't diverge. In these cases, all Git has to do is update the pointers of the branches to the same commit, and no actual merging needs to take place. On the other hand, a 3-way merge is performed when the history of the merging branches has diverged in some way, and there isn't a nice linear path to combine them via fast forwarding. This happens when a commit is made on one branch after the point when both branches split. In our case, This could have happened if we made a commit on the master branch after creating the other branches. When this occurs, Git will tie the branch histories together with a new commit and merge the snapshots at the two branch tips with the most recent common ancestor, the commit before the divergence. To do this successfully, Git tries to figure out how to combine both snapshots. If the changes were made in different files or in different parts of the same file, Git will take both changes and put them together in the result. If, instead, the changes were made on the same part of the same file, Git won't know how to merge those changes, and the attempt will result in a merge conflict. This sounds scary, but don't panic. Git doesn't quit. We'll solve those conflicts in our next video. From time to time, we might find that both the branches we're trying to merge have edits to the same part of the same file. This will result in something called a merge conflict. Normally, Git can automatically merge files for us, but when we have a merge conflict, it will need a little help to figure out what to do. To see how this would look, let's edit the free memory pie file in the master branch and replace the pass statement with a comment about what the main function should do. Cool, we made the change, so let's save it and commit it back to our master branch. Next, let's check out the even better feature branch and make a change in the same place. In this case, we'll replace the call to pass with a call to print, saying that everything is okay. Now we'll save this other change and commit it to this branch. We are primed for chaos with our file all set up for our merge conflict. Let's check out the master branch again and try to merge the even better feature back into it. Git tells us it tried to automatically merge the two versions of the free memory file, but it didn't know how to do it. We can use git status to get more information about what's going on. As usual, git status gives us a lot of additional information. It tells us that we have files that are currently unmerged and that we need to fix the conflicts or abort the merge if we decide it was a mistake. It also tells us that we need to run git add on each unmerged file to mark that the conflicts have been resolved. So let's get to work. To fix the conflict, let's open up free memory pie in our text editor. Thankfully, Git has added some information to our files to tell us which parts of the code are conflicting. The unmerged content of the file at head, remember, in this case head points to master, is the doc string stating what the main function should do. And the unmerged content of the file in the even better feature branch is the call to the print function. So it's up to us to decide which one to keep, or if we should change the contents of the file altogether. In this case, we'll keep both statements and delete the merger markers. Now that we've fixed the conflict, we'll mark it as resolved by running git add on the file, and then call the git status to see how our merge is doing. See how Git now tells us that all conflicts have been resolved? Woohoo! We just need to call git commit to wrap up the merge. The comments that git commit shows us look different than other commits. That's because this is a merge, and Git tells us so. It also tells us which file had conflicts, which have now been resolved. The commit already has a description saying that it's merging the other branch. This description was automatically created when we called the git merge command, but we can add onto this description if we want. For example, we can say that we're keeping the lines from both branches, and then just save and exit as usual. And the merge conflict is resolved. To see what the commit history looks like now, we'll use a couple of handy options to the git log command. --graph for seeing the commits as a graph, and --one line to only see one line per commit. This format helps us better understand the history of our commits and how merges have occurred. We can see the new commit that was added and also the two separate commits that we merged, one coming from the master branch and the other coming from the even better feature branch. We can also see that master is pointing to the merge commit, but even better feature is still pointing to the previous one. In our example, resolving the conflict was straightforward and easy. But in the real world, this won't always be the case. Merge conflicts can sometimes be tricky, complicated, and spread across multiple files. If you want to throw the merge away and start over, you can use the git merge --abort command as an escape hatch. This will stop the merge and reset the files in your working tree back to the previous commit before the merge ever happened. So, by now you know how to create, delete, and switch between branches in Git. You've also seen that each branch represents a pointer to a commit and a sequence of independent snapshots. And you know how to merge these commits back into the main trunk by using the git merge command. Amazing work! Seriously, this isn't easy stuff. Up next, you'll find a cheat sheet summarizing all of these branching techniques, followed by a quiz to consolidate these concepts. Well done making it all the way here. The concepts we've tackled in the past few videos were no walk in the park, but you've powered through them with flying colors. We've learned a lot more about how to interact with Git. We started with some advanced commands, like skipping the staging area, getting additional info about our commits, and being able to delete and rename files in our repository. After that, we dove into one of the main concepts of version control, the ability to undo things. We looked at how to revert unstaged and staged changes, how to amend commits, and how to perform rollbacks, whether from the latest commit or an older one. Finally, we cut through the entangled world of branching. We learned how to create, switch to, and delete branches. We looked into how to merge branches and how to solve pesky merge conflicts when they cause trouble. There's an assessment coming up to help you put all of your new skills into action. Remember that you can spend as much time as you need reviewing any of the content we've covered, until you feel ready to take on the assessments head on. I'll meet you in the next video, where we'll check out how to use and manage remote repositories. We'll also learn how to use Git in the context of a collaborative environment. See you soon. Welcome back. Up till now, we've learned a lot of interesting and complex techniques on how to use Git locally. We started with the very basic Git workflow for modifying files, staging the changes, and then committing them. We then looked at other things we can do with Git, like deleting or renaming files, getting more information about commits, or skipping the staging area altogether. Next, we saw how to undo staged, unstaged, or committed changes in our Git repositories. And finally, we learned a bit about how to work with different branches, like how to merge changes from separate branches. That's a lot of complex stuff, and it's natural that it might seem scary, but it can also be very satisfying once you start to understand what's going on. And just think of how valuable these new skills will be as you advance your IT career. So, remember that you can review the material as many times as needed, and that the best way to master it is to keep practicing on your own. In this module, we'll learn a load of new things related to GitHub and remote repositories. We'll first talk about what GitHub is and why it matters, and then we'll dive into how to work with GitHub and other remote repositories. Being able to use remote repositories allows us to effectively collaborate with others. Our collaborators can be sitting in the same office as we are, or they can be thousands of miles away on a different continent working at a different time of day. Using a version control system like Git lets us incorporate the work of different people no matter where they are or when they're working. I've personally had a bunch of interesting experiences collaborating through a version control system. One that stands out was a debugging session a friend and I had while at work. I was working on some tricky code and I couldn't figure out the best way to implement a function. I was stuck and ready to give up completely. My colleague suggested that I work on another piece of the file further down while he figured out the optimal solution for the code that I was having trouble with. This was a super seamless experience and was only possible because of a VCS. And the superpower of teamwork, of course. By the end of the module, you'll be able to collaborate with friends and colleagues just like I did. Let's get to it. In earlier videos, we called out that Git is a distributed version control system. Distributed means that each developer has a copy of the whole repository on their local machine. Each copy is a peer of the others, but we can host one of these copies on a server and then use it as a remote repository for the other copies. This lets us synchronize work between copies through this server. Any of us can create a Git server like this one, and many companies have similar internal services. But if you don't want to set up a Git server yourself and host your repositories, you can use an online service like GitHub. GitHub is a web-based Git repository hosting service. On top of the version control functionality of Git, GitHub includes extra features like bug tracking, wikis, and task management. GitHub lets us share and access repositories on the web and copy or clone them to our local computer so we can work on them. GitHub is a popular choice with a robust feature set, but it's not the only one. Other services that provide similar functionality are Bitbucket and GitLab. For the rest of this course, we'll be using GitHub for our examples, but feel free to use the tool that best fits your needs. GitHub provides free access to a Git server for public and private repositories. It limits the number of contributors for the free private repositories and offers an unlimited private repository service for a monthly fee. We'll be using a free repository for our examples, which is fine for educational use, small personal projects, or open source development. A word of caution on how you can manage these repos, though. If hackers get hold of information about your organization's IT infrastructure, they can use it to try and break into your network. So make sure you treat this information as confidential. For real configuration and development work, you should use a secure and private Git server, and limit the people authorized to work on it. To use GitHub, the first thing you need to do is create an account, if you don't have one already. Signing up online is free and relatively simple. Once you've done that, you can either create your own repos or contribute to repos from other projects. If you don't have a GitHub account yet, now is a good time to create one. Visit github.com to sign up for their service. Once you've done that, meet me over in the next video where we'll go over some basic interactions with GitHub. As we called out, GitHub is an online service, and to use it, you first need to create an account on the site. Once you have your account, you're ready to create your brand new repository on GitHub. Let's do this now, going step by step. We'll start by clicking the Create a Repository link on the left. This will take us to the repo creation wizard. The wizard is pretty straightforward. The first thing we need to do is give a name for our repo. We'll call this repo Health Checks. After that comes a description of what the repo will be used for. We'll say that it will be used for scripts that check the health of our computers. Then we need to select whether we want the repo to be public or private. We'll go with private for now. And finally, the wizard can help us get started with some few initialization files, like a README, a gitignore, or a license file. We'll go with just the README for now, and then create the repo. Yay! Using the wizard, we created the repo and have a fresh remote repository ready to go. Just like magic. Let's get to work. First step is to create a local copy of the repository. We'll do that by using the git clone command followed by the URL of the repo. GitHub conveniently lets us copy the URL from our repo from the interface so that we don't have to type it. We're now ready to clone the repo into our computer. We'll do that by calling git clone and paste in the URL we copied. To do this, GitHub will ask for our username and password. Just like that, we've downloaded a copy of the remote repository from GitHub onto the local machine. This means that we can perform all the Git actions that we've learned up till now. Since the repo is called health checks, a directory with that name was automatically created for us and now has the working tree of the repository in it. So let's change that directory and look at the contents. Our repo is basically empty. It only has the README file that GitHub created for us. This file is in a special format called Markdown. Let's add a bit more content to it. We've changed this file. What do we need to do now? We need to stage the change and commit it. We've seen a couple different ways to do that. Let's use our shortcuts to do this in just one command. Okay, we've modified our README file, but we've seen all this before. We got a remote repository set up on GitHub, so let's use it. We can send our changes to that remote repository by using the git push command, which will gather all the snapshots we've taken and send them to the remote repository. In this case, we've only taken one snapshot. We'll talk more about what's going on behind the scenes with git push and remote repositories in later videos. But the mechanics are pretty simple. To push our modified README up to GitHub, we'll just call git push. Once again, we're asked for our password. After that, we see a bunch of messages from Git related to the push. When we access our project, we see the contents of the README file. So if we check our repository on GitHub, we should see the updated message. Pretty cool, right? We've taken the local changes on our computer and pushed them up to a remote repository hosted on GitHub. You probably noticed that we had to enter our password both when retrieving the repo and when pushing changes to the repo. There are a couple ways to avoid having to do this. One way is to create an SSH key pair and store the public key in our profile so that GitHub recognizes our computer. Another option is to use a credential helper, which caches our credentials for a time window so that we don't need to enter our password with every interaction. Git already comes with a credential helper baked in. We just need to enable it. We do that by calling git config -- global credential.helper cache. Now that we've enabled the credential helper, we'll need to enter our credentials once more. After that, they'll be cached for 15 minutes. To check this, we can try out another git command, git pull, which is the command we use to retrieve new changes from the repository. We'll enter our credentials on the first call to the command, and they'll be cached, so we won't need to enter them again. With that, we've seen how to create repositories on GitHub, clone a remote repository, push changes to it, and pull changes from it. There's a lot going on behind the scenes here, and we'll dive deeper into the details and more collaboration techniques in later videos. For now, check out the next reading for a summary of this basic workflow. And then there's a quick quiz to make sure this is making sense. When we clone the newly created GitHub repository, we had our local Git repo interact with a remote repository. Remote repositories are a big part of the distributed nature of Git collaboration. They let lots of developers contribute to a project from their own workstations, making changes to local copies of the project independently of one another. When they need to share their changes, they can issue Git commands to pull code from a remote repository or push code into one. There are a bunch of ways to host remote repositories. As we called out, there is many internet-based Git hosting providers like GitHub, Bitbucket, or GitLab, which offer similar services. We can also set up a Git server on our own network to host private repositories. A locally hosted Git server can run on almost any platform, including Linux, macOS, or Windows. This has benefits like increased privacy, control, and customization. To understand remote repositories and Git's distributed nature a bit better, imagine you're working together with some friends to design a computer game. Each of you has a different portion of the game you're responsible for. One person is designing the levels, another the characters, while others are writing the code for the graphics, physics, and gameplay. All these areas will have to come together into a single place for the final product. Although your friends might work on their parts by themselves, from time to time, everyone needs to send out progress updates to let each other know what they've been working on. You'll then need to combine their work into your own portion of the project to make sure it's all compatible. Using Git to manage a project helps us collaborate successfully. Everyone will develop their piece of the project independently in their own local repositories, maybe even using separate branches. Occasionally, they'll push finished code into a central remote repository, where others can pull it and incorporate it into their new developments. So, how does this work? Alongside the local development branches like master, Git keeps copies of the commits that have been submitted to the remote repository in separate branches. If someone has updated the repository since the last time you synchronized your local copy, Git will tell you that it's time to do an update. If you have your own local changes, when you pull down the code from the remote repo, you might need to fix merge conflicts before you can push your own changes. In this way, Git lets multiple people work on the same project at the same time. When pulling new code, it will merge the changes automatically if possible, or will tell us to manually perform the integrations if there are conflicts. So, when working with remotes, the workflow for making changes has some extra steps. We'll still modify, stage, and commit our local changes. After committing, we'll fetch any new changes from the remote repo, manually merge if necessary, and only then we'll push our changes to the remote repo. Git supports a variety of ways to connect to a remote repository. Some of the most common are using the HTTP, HTTPS, and SSH protocols and their corresponding URLs. HTTP is generally used to allow read-only access to a repository. In other words, it lets people clone the contents of your repo without letting them push new contents to it. Conversely, HTTPS and SSH both provide methods of authenticating users, so you can control who gets permission to push. If all this protocol talk is making your head spin, you might want to review the video on these subjects made by my colleague Gian. You'll find a link to this in the next reading. The distributed nature of the work means that there are no limits to how many people can push code into a repository. It's a good idea to control who can push code to your repos and to make sure you give access only to people you trust. Web services like GitHub offer a bunch of different mechanisms to control access to repositories. Some of these are available to the general public, while others are only available to enterprise users. Okay, by now you have an idea of what a remote repository is and how it interacts with local Git repositories. Up next, we'll dive into some of the commands that let us interact with remotes. When we call git clone to get a local copy of a remote repository, Git sets up that remote repository with the default origin name. We can look at the configuration for that remote by running git remote-v in the directory of the repo. Here we see the URLs associated with the origin remote. There are two URLs. One will be used to fetch data from the remote repository, and the other one to push data to that remote repo. They'll usually point at the same place. But in some cases, you could have the fetch URL use HTTP for read-only access, and the push URL use HTTPS or SSH for access control. This is fine as long as the contents of the repo that you read when fetching are the same that you write to when pushing. Remote repositories have a name assigned to them. By default, the assigned name is origin. This lets us track more than one remote in the same Git directory. While this is not the typical usage, it can be useful when collaborating with different teams on projects that are related to each other. We won't look at how to do that here, but we'll include a link for more information in the next reading. If we want to get even more information about our remote, we can call git remote show origin. There's a ton of information here, and we don't need all of it right now. We can see the fetch and push URLs that we saw before, and the local and remote branches too. For now, we only have a master branch that exists locally and remotely, so the information here seems a bit repetitive. Once you start having more branches, especially different branches, in the local and remote repo, this information starts becoming more complex. So, what are these remote branches that we're talking about anyways? Whenever we're operating with remotes, Git uses remote branches to keep copies of the data that's stored in the remote repository. We can have a look at the remote branches that our Git repo is currently tracking by running git branch-r. These branches are read-only. We can look at the commit history like we would with local branches, but we can't make any changes to them directly. To modify their contents, we'll have to go through the workflow we called out before. First, we pull any new changes to our local branch, then merge them with our changes and push our changes to the repo. Remember how we've been using git status to check the status of our changes? We can also use git status to check the status of our changes in remote branches as well. Now that we're working with a remote repository, git status gives us additional information. It tells us that our branch is up to date with the origin/master branch, which means that the master branch in the remote repository called origin has the same commits as our local master branch. But what if it wasn't up to date? We'll talk about that in the next video. While we were learning about remotes, our colleague Blue Kale added some files to our repo. We could always use the GitHub website to browse the changes that were submitted. But we want to learn how to do it by interacting through the command line because you might need to do it this way at your job, and it'll work the same no matter which platform you use to interact with Git. So, first, let's look at the output of the git remote show origin command. Check out how it says that the local branch is out of date. This happens when there were commits done to the repo that aren't yet reflected locally. Git doesn't keep remote and local branches in sync automatically. It waits until we execute commands to move data around when we're ready. To sync the data, we use the git fetch command. This command copies the commits done in the remote repository to the remote branches, so we can see what other people have committed. Let's call it now and see what happens. Fetched content is downloaded to the remote branches on our repository, so it's not automatically mirrored to our local branches. We can run git checkout on these branches to see the working tree, and we can run git log to see the commit history. Let's look at the current commits in the remote repo by running git log origin/master. Looking at this output, we can see that the remote origin/branch is pointing to the latest commit, while the local master branch is pointing to the previous commit we made earlier on. Let's see what happens if we run git status now. Git status helpfully tells us that there's a commit we don't have in our branch. It does this by letting us know our branch is behind the remote origin/master branch. If we want to integrate the branches into our master branch, we can perform a merge operation, which merges the origin/master branch into our local master branch. To do that, we'll call git merge origin/master. Great, we've merged the changes of the master branch of the remote repository into our local branch. See how Git tells us that the code was integrated using fast forward? It also shows that 2 files were added, allchecks and diskusage.py. If we look at the log output on our branch now, we should see the new commit. We see that now our master branch is up to date with the remote origin/master branch. And with that, we've updated our branch to the latest changes. We can use git fetch like this to review the changes that happened in the remote repository. If we're happy with them, we can use git merge to integrate them into the local branch. Fetching commits from a remote repository and merging them into your local repository is such a common operation in Git that there's a handy command to let us do it all in one action. We'll check that out in our next video. Earlier, we took a look at the basic workflow for working with remotes when we want to fetch the changes manually, merge if necessary, and only then push any changes of our own. Since fetching and merging are so common, Git gives us the git pull command that does both for us. Running git pull will fetch the remote copy of the current branch and automatically try to merge it into the current local branch. Let's check if our friend Blue Kale has made any new changes to the repo. We'll run git pull and see what changes we get. If you look closely at this output, you'll see that it includes the output of the fetch and merge commands that we saw earlier. First, Git fetched the updated contents from the remote repository, including a new branch, and then it did a fast forward merge to the local master branch. We'll see that the allchecks file was updated as well. We can look at the changes by using git log-p-1. We see that our colleague added a check disk full function that includes the code from the other diskusage.py file that we saw earlier. So now I'll exit the editor with Q. When we called git pull, we saw that there was also a new remote branch called experimental. Our friend Blue Kale told us that they've started working on a new feature in that branch. Let's check out the output of git remote show origin and see what it says about that new branch. We see that there's a new remote branch called experimental, which we don't have a local branch for yet. To create a local branch for it, we can run git checkout experimental. When we checked out the experimental branch, Git automatically copied the contents of the remote branch into the local branch. The working tree has been updated to the contents of the experimental branch. Now we're all set to work on the experimental feature together with our colleague. In this last example, we got the contents of the experimental branch together with those of the master branch when we called git pull, which also merged new changes onto the master branch. If we want to get the contents of remote branches without automatically merging any contents into the local branches, we can call git remote update. This will fetch the contents of all remote branches so that we can just call checkout or merge as needed. We've now seen a bunch of different ways that we can use to interact with remote repositories. We've seen how to check their status, how to push and pull changes into repositories, and even how to get new branches out of them. There's still more to come, but you're probably starting to see how useful this can be for collaborating with others. In our past examples, we've only looked at what happens with changes when they can be solved through fast forward. In upcoming videos, we'll look at what happens when we try to push changes, especially when our changes generate conflicts. But before we do that, check out the reading for the list of all the commands involved and then take the quiz to put this knowledge into practice. We've now looked at the details of fetching and pulling data from remote repositories without any local changes. We saw earlier how we can use the git push command to send our changes to the remote repo. But what if when we go to push our changes, there are new changes to the remote repo? To find out, let's start by making a change to our allchecks.py script. Remember way back at the beginning of the course when we fixed the bug in the function that checks the disk space? The one that was doing gigabyte conversion twice? Part of the reason why our code was so buggy was that we were passing numbers around without saying what those numbers were for. We could have made our code clearer by renaming our min absolute parameter to min GB, so that it's obvious that the function expects gigabytes. With that, we've clarified the code of the function. Another way we can make the code invocation clearer, we can use the name of the parameters in the call to the function, like this. By using the names of the parameters, our invocation is clear and we could even alter the order of the values and our code would still work. Alright, we've made the change. Let's stage it and commit it as usual. We'll first use git add-p to look at the changes we made and accept them. Then we'll create a commit message to show that we've renamed min absolute to min GB and that we're using parameter names for the invocation. We've made our change, staged it, and committed it. We should be ready to push into the remote repo. Except now we have a collaborator also making changes. Let's see what happens when we try running git push. And it failed. Can you work out what went wrong here? There are a few hints. When we tried to push, Git rejected our change. That's because the remote repository contains changes that we don't have in our local branch that Git can't fast forward. Maybe you remember when we talked about Git's merging algorithms? As usual, Git gives us some helpful information along with the error message, especially the part about integrating remote changes with Git pull. This means we need to sync our local remote branch with the remote repository before we can push. We learned earlier that we can do this with Git pull. Let's do this now. Git tried to automatically merge the local and remote changes to all checks pi, but found a conflict. Let's first look at the tree of commits on all branches as represented by git log --graph --oneline --all. This graph shows us the different commits and positions in the tree. We can see the master branch, the origin/master branch, and the experimental branch. The graph indicates that our current commit and the commit in the origin/master branch share a common ancestor, but they don't follow one another. This means that we'll need to do a three-way merge. To do this, let's look at the actual changes in that commit by running git log-p origin/master. So, our colleague decided to reorder the conditional clauses in the function to match the order that the parameters are passed to the function. They happen to change the same line that we changed when we renamed the min_GB variable, which caused a conflict that Git couldn't resolve. Let's fix it by editing the file to remove the conflict. So first, let me exit with Q. We see that the problem occurred in the conditional. On the first line, we see our change, where min_absolute was renamed to min_GB. In the second line, we see the old variable names, with the checks done in a different order. We need to decide what to do to this. For example, we can keep the new order, but use min_GB. One thing to notice is that Git will try to do all possible automatic merges and only leave manual conflicts for us to resolve when the automatic merge fails. In this case, we can see that the other changes we made were merged successfully without intervention. Only the change that happened in the same line of the file needed our input. We fixed the conflict here, and the file is short enough that we can very quickly check that there are no other conflicts. For larger files, it might make sense to search for the conflict markers greater than in the whole file. This lets us check that there are no unresolved conflicts left. Nice. Now that we've fixed the conflict, you can finish the merge. Do you remember how to do it? We need to add the allchecks.py file and then call git commit to finish the merge. But first, we're going to save and close. The editor message shows that it's performing a merge of the remote branch with the local branch. We can add extra information to this message. For example, we can say that we fixed the conditional in the check disk usage function to use the new variable name and the new order. Our merge is finally ready. We can try pushing to the remote again. Yes! After fixing the conflict, we were able to push our work to the remote repo. Let's look at the commit history of the master branch now by calling git log --graph --oneline. We see that the latest commit is the merge, followed by the two commits that cause the merge conflict, which are on split paths in our graph. As we called out before, when Git needs to do a three-way merge, we end up with a separate commit for merging the branches back into the main tree. Now we know how to successfully complete a pull, merge, and push cycle, even when it means doing some manual merges. This was a complex exercise, and it's okay if some things still seem a bit scary. We all felt panicked the first time we encountered a merge conflict, but don't worry, it gets easier with practice. To practice dealing with merge conflicts, you want to have 2 copies of your repository in separate directories, then try editing the same lines of the same files. You can follow along with the examples shown here, or come up with your own. Up next, we'll talk about using branches with remote repositories. As we called out before, when using Git to work on a new feature or a big refactor of some kind, it's recommended best practice to create separate branches. There are many advantages to doing this. For example, it might take you a while to finish the new feature, and in the meantime, there could be a critical bug that needs fixing in the main branch of the code. By having separate branches, you can fix the bug in the main branch, release the new version, and then go back to working on your feature without having to integrate your code before it's ready. Another advantage of working in separate branches is that you could even release 2 or more versions out of the same tree, one being the stable version and the other being the beta version. That way, any disruptive changes can be tested on a few users or computers before they're fully released. So let's start a new branch to work on a small refactor of our code. Do you remember how to do that? You could create the branch first and then check it out, or we can just create it and check it out with git checkout-b and the new branch name. We're ready to start working on our refactor. Let's open up the file and have a look at it. We've noticed there's a pattern of repeating code in our all checks py script. For each check that we call, we check if it returns true or false. When it returns true, we print an error and exit. If we add a new check, we'll have to repeat this pattern again. On top of the repeated pattern, if a computer has more than one problem, only the error for the first one will be printed. So let's refactor our code to avoid the duplication and print all relevant errors. We'll do it step by step, making each commit self-contained. The first thing we'll do is create a function that checks if the disk is full without any parameters, so it matches the pattern. This new wrapper function will pass the right parameters for us, and then we'll change the code to call this function instead. We'll also change the error message to something more accurate. We've changed the function. Let's save and test our code. Awesome! It's working. Let's commit the change. we're ready for the next step in our refactor. To avoid code repetition, we'll create a list containing the names of the functions that we want to call, and then message to print if the function succeeds. After that, we'll add a for loop that iterates over the lists of checks and messages. Then we'll call check, and if the return value is true, print the message and exit with an error code of 1. After doing that, we can delete the old code that we've already replaced. Phew! With this change made, let's save once again and test that our script still runs. Yes, it's still working. Let's commit the new change. By now, we've refactored our code to avoid code duplication. The current code does the same as the old code. Once we're ready to add new checks, we can do that by adding the function name and error message to the list of checks. The last change that we want to do is to let our script show more than one message if more than one check is failing. To do that, we add a Boolean variable called everything-okay before the iteration. Change this variable to false if one of the checks finds a problem, and then exit with an error code only after having done all the checks. All right, one last time. Let's save and test to see if this works. And let's now do a final commit for this change. With that, we have 3 commits in our refactor branch. Before we merge any of this into the master branch, we want to push this into the remote repo so that our collaborators can view the code, test it, and let us know if it's ready for merging. The first time we push a branch to a remote repo, we need to add a few more parameters to the git push command. We'll need to add the -u flag to create the branch upstream, which is another way of referring to remote repositories. We'll also have to say that we want to push this to the origin repo and that we're pushing the refactor branch. Whoa, that's a lot of information that Git's giving us. It's telling us if we want, we can create a pull request. We'll talk more about pull requests later on. For now, we're happy to see that the new refactor branch has been created in the remote repo, which is what we wanted. This was a super complex example that incorporated a lot of concepts that we've learned about in this course, and also carried out some interesting Python concepts. If anything is still unclear, feel free to re-watch this video and follow along on your computer until you're comfortable with these steps. So, now that our branch is pushed to the remote repo, it can be reviewed by our collaborators. Assuming they say it's okay, how should this branch get merged back into the master branch? We'll talk about that in our next video. In our last video, we mentioned that once our branch has been properly reviewed and tested, it can get merged back into the master branch. This can be done by us or by someone else. One option is to use the git merge command that we discussed earlier. Another option is to use the git rebase command. Rebasing means changing the base commit that's used for our branch. To understand what this means, let's quickly recap what we've learned about merges up till now. As we've seen in a lot of our earlier examples, when we create a branch at a certain point in the repo's history, Git knows the latest commit that was submitted on both branches. If only one of the branches has new changes when we try to merge them, Git will be able to fast forward and apply the changes. But if both branches have new changes when we try to merge, Git will create a new merge commit for the three-way merge. The problem with three-way merges is that because of the split history, it's hard for us to debug when an issue is found in our code, and we need to understand where the problem was introduced. By changing the base where our commits split from the branch history, we can replay the new commits on top of the new base. This allows Git to do a fast forward merge and keep history linear. So, how do we do it? We run the command git rebase followed by the branch that we want to set as the new base. When we do this, Git will try to replay our commits after the latest commit in that branch. This will work automatically if the changes were made in different parts of the files, but will require manual intervention if the changes were made in other files. Let's check out this process by rebasing our refactor branch onto the master branch. First, we'll check out the master branch and pull the latest changes in the remote repo. Git tells us that it's updated the master branch with some changes that our colleague had made. At this point, the changes that we have in the refactor branch can no longer be merged through fast forwarding into the master branch. That's because there's now an extra commit in the master that's not present in the refactor. Let's see how this looks by asking the log command to show us the current graph of all branches. It might take a bit to follow everything that's going on with this graph, but it can be really useful to understand complex history trees. As you can see, the refactor branch has 3 commits before the common ancestor with the current commit that's at the head of the master branch. If we merged our branch now, it would cause a 3-way merge, but we want to keep our history linear. We'll do this with a rebase of the refactor against master. As usual, Git gives us a bunch of helpful information. It says that it rewound head and replayed our work on top of it. And luckily, everything succeeded. Let's look at the output of git log -graph -1 line for our branch right now. Now we can see the master branch in linear history with our list of commits. We're ready to merge our commits back onto the main trunk of our repo and have this fast forwarded. To do that, we'll check out the master branch and merge the refactor branch. Awesome! We were able to merge our branch through a fast forward merge and keep our history linear. We're now done with our refactor and can get rid of that branch, both remotely and locally. To remove the remote branch, we'll call git push --delete origin refactor. To remove the local branch, we'll call git branch -d refactor. Yes! We're done with our refactor. We can now push changes back into the remote repo. Alright, we've just gone through an example using the git rebase command. We had a feature branch created against an older commit from master, so we rebased our feature branch against the latest commit from master and then merged the feature branch back into master. That was a complicated exercise, so if you're still confused about what's going on, take your time to review, and maybe come up with your own examples when you'd use a rebase. Up next, we'll look at another example of how to use a rebase. In our last video, we looked at an example use case for Git rebase, where we used it to rebase a feature branch so that it could be cleanly integrated. There are many other possible uses of rebase. One common example is to rebase the changes in the master branch when someone else also made changes, and we want to keep history linear. This is a pretty common occurrence when you're working on a change that's small enough not to need a separate branch, and your collaborators just happen to commit something at the same time. Let's check out how this would work in practice. First, we'll make a change to our script. Now that we've made it easy to add new checks, we'll add a check to warn when there's no working network. There's a ton of things to check for this, but for now, we'll keep it simple and just check whether we can resolve the google.com URL. To do this, we'll use the socket module. We'll add a new function called checkNoNetwork that will return true if it fails to resolve the URL and false if it succeeds. The socket.getHostByName function raises an exception on failure. So we'll use a try except block to wrap the call to the function and return false when the call succeeds or true when it fails. With this new function defined, we can now add the check to our list of checks. We'll just add the name of the function, and the message will be no working network. Okay, we've made the change. Let's save it and commit it. Once more, we'll use the git commit-a shortcut and pass a message saying that we've added a simple network connectivity check. We want to check if one of our teammates also made a change in the master branch while we were working on our change. In an earlier video, we showed how to do that by running git pull, which will automatically create a three-way merge if necessary. In this example, we want to look at a different approach to keep our project history linear. So we'll start by calling git fetch, which you might remember will put the latest changes into the origin/master branch, but we won't apply them to our local master branch. We see that we've fetched some new changes. This means that if we tried to merge our changes, we'd end up with a three-way merge. Instead, we'll now run git rebase against our origin/master to rebase our changes against those made by our colleague and keep history linear. Uh-oh, we've got a conflict and we'll need to fix it. Git is giving us a lot of info on what it tried to do, including what worked, what didn't work, and what we can do about it. Since we asked it to rebase, it tried to rewind our changes and apply them on top of what was in the origin/master branch. The first commit made by our colleague renamed allchecks.py to healthchecks.py. Git detected this and automatically merged our changes into the new file name. But when trying to merge our changes with the changes made by our colleague in the file, there was a merge conflict. The output gives us a bunch of instructions on how to solve this. We could fix the conflict, skip the conflicting commit, or even abort the rebase completely. In this example, we want to fix the conflict. So let's do that. We'll start by looking at the current state of the healthchecks.py file. We see that while we were adding the connectivity check, our colleague was adding a check for the CPU being constrained. We want both functions in the end result, so let's remove the conflict markers, cleaning up our file. All right, This looks good. Let's save and test our script out. Ah, so close. It looks like our colleague forgot to import the psutil module. Let's do that now. All right, let's hope this works. Yes, we fixed the conflict and our script is working again. We now need to add the changes made to the health checks py file and continue with the rebase. Now the rebase has finished successfully. Let's check out the output of git log -graph -1 line to see what the history looks like at this point. We see that we've applied our change on top of the other changes without needing a three-way merge. What we did just now to resolve the conflict is very similar to what we did earlier to merge our changes. The difference is that the commit history ended up being linear instead of branching out. We're now ready to push our new check to the remote repo. In this example, we've seen how we can use the fetch, rebase, push workflow to merge our changes with our collaborators' changes, while keeping the history of our changes linear. As we called out, keeping history linear helps with debugging, especially when we're trying to identify which commit first introduced a problem in our project. We've now seen two examples of how to use the git rebase command, one for merging feature branches back into the main trunk of our code, and one for making sure that our commits made in the master branch apply cleanly on top of the current state of the master branch. And it doesn't stop there. We can also use git rebase to change the order of the commits, or even squash two commits into one. This is a very powerful tool, but don't worry, you don't need to memorize all of its possible uses. You'll learn them as you need them. Up next, we'll do a roundup of some of the best practices for operating with Git when collaborating with others. Over the past few videos, we've looked at a lot of things we can do with Git and remote repositories. It's worth spending some time talking about best practices for collaborating with others. It's a good idea to always synchronize your branches before starting any work on your own. That way, whenever you start changing code, you know that you're starting from the most recent version and you minimize the chances of conflicts or the need for rebasing. Another common practice is to try and avoid having very large changes that modify a lot of different things. Instead, try to make changes as small as possible, as long as they're self-contained. For example, if you're renaming a variable for clarity reasons, you don't want to have code that adds new functionality in the same commit. It's better if you split it into different commits. This makes it easier to understand what's going on with each commit. On top of that, if you remember to push your changes often and pull before doing any work, you reduce the chances of getting a conflict. We called out already that when working on a big change, it makes sense to have a separate feature branch. This lets you work on new changes while still enabling you to fix bugs in the other branch. To make the final merge of the feature branch easier, it makes sense to regularly merge changes made on the master branch back onto the feature branch. This way, we won't end up with a huge number of merge conflicts when the final merge time comes around. If you need to maintain more than one version of a project at the same time, it's a common practice to have the latest version of the project in the master branch and a stable version of the project on a separate branch. You'll merge your changes into the separate branch whenever you declare a stable release. When using these two branches, some bug fixes for the stable version may be done directly on the stable branch if they aren't relevant to the latest version anymore. In the last couple of videos, we looked at how we can use rebase to make sure our history is linear. Rebasing can help a lot with identifying bugs, but use it with caution. Whenever we do a rebase, we're rewriting the history of our branch. The old commits get replaced with new commits, so they'll be based on different snapshots than the ones we had before, and they'll have completely different hash sums. This works fine for local changes, but can cause a lot of trouble for changes that have been published and downloaded by other collaborators. So, as a general rule, you shouldn't rebase changes that have been pushed to remote repos. The Git server will automatically reject pushes that attempt to rewrite the history of the branch. It's possible to force Git to accept the change, but it's not a great idea unless you really know what the implications will be. In our feature branch example, we rebased the branch, merged it to the master, and then deleted the old one. That way, we didn't push the rebase changes to the refactor branch, only to the master branch that hadn't seen those changes before. Early in our Git journey, we mentioned that having good commit messages is important. It's already important when you're working alone, since good commit messages help the future you understand what's going on. But it's even more important when you're collaborating with others, since it gives your collaborators more context on why you made the change and can help them understand how to solve conflicts when necessary. So commit to being a good collaborator and remember to add those commit messages. Whenever we collaborate with others, there's bound to be some merge conflicts, and they can sure be a pain. I've definitely been frustrated when encountering complex merge conflicts and trying to debug the results. If I'm dealing with this type of merge conflict, my first step is to work backward and disable everything I've done and then see if the source still works. Then I slowly add pieces of code until I hit the problem. That usually gets me through the tough times and has definitely highlighted some weird occurrences. Up next, we have a reading that puts together all the commands related to solving conflicts, and then a quick practice quiz. Before we start, congratulations on making it all the way here. We've covered some complex subjects, and you're showing a lot of dedication by making it to this point. Let's review what we've learned in the last few videos about working with remotes in Git. First, we talked about what GitHub is and what the basic interaction with the service looks like. Then, we discussed how remote repositories and the distributed nature of Git lets lots of contributors develop a project independently and at the same time. We then learned how to pull data down from remote repositories, push our local changes to them, and also resolve conflicts that pop up when our local and remote branches are out of sync. We wrapped up by looking at a complex example of using a feature branch for a refactor of our code and using rebase to make sure that our history stayed linear. That was a lot of info, and you might be feeling a bit overwhelmed. It's okay to feel that way. Learning how to use a VCS like Git can be difficult, but the rewards are worth the effort. Remember that version control systems give you access to the history of any scripting project, fostering collaboration and accountability, and making it possible to do fast rollbacks. Using an understanding of VCS is a valuable and versatile skill for every IT specialist, and one that will set you apart from the crowd. Coming up, the graded assessment will let you put all of this new knowledge to practice. As we called out before, feel free to review as much as you need, and when you're ready, head over to the graded assessment. You've got this. Welcome back. Over the past modules, we've learned a whole lot about how to interact with Git. We've covered how to use it both locally and remotely. We've seen how to roll back bad changes, solve conflicts when collaborating with others, and a bunch of other little nifty things. In this module, we'll keep exploring the collaboration tools available in Git. We'll learn about tools that allow us to send changes to projects that we aren't a member of, help us improve the quality of our code, and let us track our work better. Some of these tools will be specific to GitHub, but most of the Git repository hosting services have similar tools, so the concepts will still apply if you decide to use a different platform. In recent years, GitHub has become a super popular platform for collaboration across many projects. It's used heavily for open source projects. These are projects that allow anyone to use, copy, and modify their code. Having the code published online means that anybody in the world can learn from what the project is doing, and even collaborate on fixes and extra features. It also helps us learn from each other because we can look at how others have solved the problem that we're tackling. I regularly use GitHub to look up code snippets for things that I'm interested in. Most recently, I looked up examples for a movie theater seat finder because I was working on a similar feature for a personal project of mine. If you're trying to learn a new technology, it's a great idea to practice your skills by contributing to a project that uses that technology. To do that, you'll need to know how to interact with the project. This includes how to send bug fixes, how to make sure that your fixes are applied, and even how to figure out which fixes are needed. In this module, we'll cover that and a lot more. So are you excited? I'm excited. Let's get started. As we called out, we can use GitHub to look at other people's code and collaborate with them. Let's see this in action by having a look at one of the projects from our colleague Blue Kale. Okay, so our colleague has created a project to include all validation functions. Let's have a look at the validations py file. We can see the code of a function that validates a username. But, if you look closely at the function's documentation, you might notice that there's a typo. We can improve our colleague's code by fixing that typo. Let's do that. We'll click on the little pencil icon, which lets us edit the file directly from the web interface. We're trying to edit a file in a project that we don't have write access to. GitHub tells us it created a fork of this project for us, which we can commit our changes to. And if we submit changes to this file, it will create a new branch so that we can send a pull request. But what exactly is a fork? Forking is a way of creating a copy of the given repository so that it belongs to our user. In other words, our user will be able to push changes to the fork copy even when we can't push changes to the other repo. When collaborating on projects hosted on GitHub, the typical workflow is first create a fork of the repo and then work on that local fork. A forked repo is just like a normal repo, except GitHub knows which repo it forked from, so we can eventually merge our changes back into the main repo by creating a pull request. A pull request is a commit or series of commits that you send to the owner of the repository so that they incorporate it into their tree. This is the typical way of working on GitHub because in most projects, only a few people have commit rights to the repo, but anybody can suggest patches, bug fixes, or even new features by sending pull requests that people with commit access can then apply. Typically, the owners of the repo will review the changes before merging them, checking that they match the development guidelines for the project and that the license is valid and so on. Let's fix the typo in the file to see what the pull request looks like. Once we're done making changes to the file, we can make a change proposal by scrolling down and filling in the description of the change. In this case, we fixed the typo in the function documentation. Clicking on the proposed file change button will create a commit in our forked repo so that we can send the change to our colleague. Let's do that now. We've created a commit on our forked repo, but we haven't yet created the pull request that will send the changes to the owner of the original repo. On this screen, we can see a lot of information about our change. We can see what repositories and branches are involved in the creation of the pull request. We can also see that GitHub automatically created a branch called patch-1 for us, and that our change can automatically be merged. Yay, no conflicts. This window also lets us review the change before we create an actual pull request. Once we're ready, we just click the Create Pull Request button. This opens a text box where we can enter comments about our change. In this case, our change was really simple. We just fixed a typo, so there's nothing extra to add. If we were suggesting a more complex change, we could use this text box to provide more context. The checkbox at the bottom lets us allow edits from maintainers. This can be useful. For example, if by the time a project maintainer gets around to merging our change, there's been more commits, and our change needs rebasing. By allowing edits, the maintainer can do it themselves instead of asking us to do it. Less work? Yes, please. Okay, we're ready. Let's click Create Pull Request. Cool. We've created a pull request with our change. Our colleague can now look at it and decide whether they want to merge it to the project or not. In this video, we checked out the simplest way of making pull requests, which is doing them directly through the GitHub interface. By using this workflow, you can already start contributing to projects on GitHub. Up next, we'll see how to do more complex pull requests. In our last video, we saw how to create pull requests directly on GitHub by using the web interface to edit files. This works for simple changes like fixing typos or adding documentation to a function. But it's not so great for making larger changes that we want to preview or test. To do that, we'll normally have a local copy of the repo in our computer and work with the forked repo as a remote. We'd need to use all the Git commands that we've learned up till now to do this. Let's check out this process by creating a fork of another repo. On top of the validations repo, our colleague Blue Kale has created a rearrange repo, and we want to help them out. We'll go to their rearrange repo and create a fork by pressing the fork button. It takes a few seconds to create a copy of the repo for our user. The copy will contain the current state of the repo, including files and commit history. Once the fork's created, we're shown a page that corresponds to the same repo name, but it's under our user. See how it shows that it's a forked repo by stating the original repo under the name? All right, we've created a forked version of the repo on GitHub. We can now get a local copy of the repo on our computer by copying the URL and then calling the git clone command with it. We now have a new directory called rearrange with the contents of the repo. We can look at the contents by changing into that directory and listing all files. And we can look at the commit history using our old friend git log. Now that we have a local copy of the repo, we can make any changes we'd like to it. For example, this project doesn't currently have a readme.md file. Let's improve the documentation by creating that. To do that, we'll create a new branch called add readme. Do you remember how to create new branches? We do it by running git checkout-b add-readme. All right, we can now start editing the readme.md file. The MD extension indicates that we're using Markdown, which is a lightweight markup language. We can use it to write plain text files that are then formatted following some simple rules. In this case, we'll start with a title with the module's name and a brief description that says it's used to rearrange names. All right, our README file is small, but it'll do for now. Let's save it and commit it. Now, to push the change to our forked repo, we need to create the corresponding remote branch. Do you remember the command for that? Yep, it's git push-u origin add-readme. So, when we push the change to the new branch, we got a message that we can create a pull request if we want to. We'll do that in a minute. First, let's check out how our file looks when rendered. Yes, our README file rendered successfully. We're ready to create a pull request for our change. To do that, let's look at the top of the project page. GitHub tells us that our branch is ahead of the original repository's master branch by one commit, which is the commit we just made. We can start our pull request by clicking on the pull request link. As we called out, before creating a pull request, it's always important to check that the code will merge successfully. GitHub tells us that our change can be automatically merged, which is great news. If this wasn't the case, we'd need to rebase our change against the current branch of the original repo so that it could be merged. The window's showing us the text box where we can enter comments about our change. As we mentioned before, we should use this to explain why we're creating this pull request. This lets the person that will approve the change understand why they should merge the change into the main tree. Are we fixing a bug? Is this a new feature to let the project support more use cases? How will the project benefit from including our change? Whatever info might be useful to the approver, record it here. We can also use this box to explain how the change was tested. If the project includes automatic test infrastructure, our pull request should include a test for our changes, and we can state that all tests still pass. But if there's no automatic testing, then we can use this box to explain how we tested the change manually. In this case, we've just added a README file that the project was missing before. So, we'll just say we're adding a README file that was missing for the project. We should also check that the change we're sending looks correct. And it's always a good idea to double check that we're sending the right change. To do that, let's look at the diff that appears at the bottom of the page. Yep, that's exactly what we want. All right, we're ready. Let's click the Create Pull Request button. Awesome! We've created our second pull request. The number next to the name of our pull request is the identifier that's used in GitHub to track issues and pull requests. We can use this identifying number to access this pull request anytime we need it. But why would we need to access a pull request after we send it? It's pretty common for project maintainers to come back with questions, comments, or even ask us to fix our pull requests. Imagine you've just finished preparing a pull request for a great new feature and you get a comment saying that it's missing some documentation. What would you do? We'll talk about that in our next video. When we send a pull request, it's pretty common to receive some comments from the project maintainers asking for some improvements. The improvement could be to add documentation or tests. Or maybe we need to make sure that change works for all cases or that it follows the project's style guidelines. There's nothing wrong with getting these comments. It actually shows the project maintainers are interested in our change. To get our change approved, it's important that you address the comments. So, if we're asked to add documentation, for example, we go and do it. So, back to our change. Looks like we got a comment from one of our colleagues. We got a comment saying that our README was too short and they'd like us to add an example. To address this comment, we'll add more details to our file. We'll start by explaining that the function rearranges last name first name into first name last name. And then we'll add an example. We'll say that calling rearrange name with Turing, Allen as a parameter will return Alan Turing. Okay, we've fleshed out the README file a bit. Now we can add our changes and commit them to the repo as usual. Let's run git commit and pass a commit message saying that we've added more information to the README. And after that, we'll push the change to the repo. All right, now that we've pushed our change back to the repo, let's check our pull request in GitHub. In the Commits tab, we can see our 2 commits. Our commit now shows up as a part of the same pull request. It's important to notice here that we just pushed our commit to the same branch as before, and GitHub automatically added it to the pull request. If we wanted to create a separate pull request, we would need to create a new branch instead. If we go to the Files Changed tab, we can see all files affected by the pull request, no matter which commit they were changed in. Whenever we look at the diff generated by a commit or a chain of commits, GitHub will show a colored diff for the changes that we've made. It'll use green for new lines and red for lines that were deleted. If only a part of the line changed, it will highlight that specific part of the line. In this case, it's a new file, so all the lines are additions. Check out how we see only one file even when there are 2 separate commits. What we're seeing is the difference between our repo and the original repo we created the pull request for. We can also click on the preview icon and show the rendered markdown contents. GitHub renders our file and highlights the changes. Keep in mind that each project in GitHub may work slightly differently. Some projects may ask you to have only 1 commit in your pull requests. Other projects may ask you to rebase against the latest master branch when your pull request is ready to be merged back into the main tree. GitHub allows projects to set their contribution guidelines. You'll find a link to them whenever you create a new pull request or issue in a project. So, make sure you've read these guidelines and that your pull requests match them. In this video, we saw how to update our pull requests by doing new commits in our local Git repository and pushing them to the remote repository. We'd seen before how to use the Git web interface to create new pull requests, and we can use this interface to update a pull request. This can be handy when the change that we want to make is small, like fixing a typo or adding an extra sentence to the documentation. Up next, we'll talk about what to do if you're asked to squash your changes into a single commit. As we've called out before, you shouldn't rewrite history when the commits have been published. That's because someone else may have already synchronized their repo with those contents. This rule is waived with pull requests, since it's usually only you who'll have cloned your fork of the repository. So, say the project maintainers ask us to create a single commit that includes both changes and a more detailed description than the one we submitted. We can do that by using the interactive version of the rebase command, called rebase-i. As the parameter to the command, we'll pass the master branch. So, we'll call git rebase-i master. When we call an interactive rebase, a text editor opens with a list of all the selected commits, from the oldest to the most recent. By changing the first word of each line, we can select what we want to do with the commits. The default action here is pick, which takes the commits and rebases them against the branch we selected. This is what we did with git rebase in an earlier video, when we called it without the -i flag. But now we can change the action to something else. The comments in the file tell us all the different commands we can use for our commits. For example, we can reword a commit message, keeping the changes as they are, but modifying the commit message. We can also edit the commit to add or remove changes from it. We have 2 options for combining commits, squash and fix up. In both cases, the contents of the selected commit are merged into the previous commit in the list. The difference is what happens with the commit messages. When we choose squash, the commit messages are added together and an editor opens up to let us make any necessary changes. When we choose fix up, the commit message for that commit is discarded. For our example, we want to use squash so that we can combine both commits, but also modify the commit description. So, let's change the pick command in the second line to squash it into the first one. Then we'll save and exit the editor as usual. Once we've told Git that we want to squash a commit onto the one before it, we're given another file to edit. In this case, it's the combined commit message. As usual, Git shows us some helpful information in the comments, including which files are modified and what commits are being combined. We want to improve the description by adding more info about our change. Let's add we're including an example use case. All right, now that our commit contains the right information, we can save and exit as usual. Yes, our rebase worked. Let's check the output of Git show to see the latest commit and the changes in it. Success! We got exactly what we wanted here. Our two changes have been combined into one that contains the whole new file and the right commit message. Before we try to push this change to our repo, let's call git status to check the info that Git gives us about the current state. Git tells us that our local branch has one commit, which is the rebase we just did. It also tells us that the origin/add-readme branch has two commits. These are the two commits we had already pushed to the repo. Let's look at the graph history of our commits by calling git log --graph --oneline --all for all branches, and -4 for just the latest 4 commits. We can see that the two commits pushed to the origin/add-readme branch show up in a different path than the commit that's currently in our local add-readme branch. This is expected whenever we do a rebase because the old commits are in the remote repo and we have a different commit in our local repo. What do you think will happen when we call git push? Let's try that out. As we expected, Git doesn't like us trying to push our change because it can't be fast forwarded. But in this case, we don't want to create a merge. Instead, we want to replace the old commits with the new one. To do this, we'll call git push-f to force Git to push the current snapshot into the repo as is. Woohoo! This time, our push completed successfully. Git tells us here that we forced an update. Let's look once again at our history graph by running git log --graph --oneline -all -4. This time, it's just one commit on top of master. The divergence is gone. Now, let's look at the contents of the pull request. Success! We've managed to combine both our commits into one by using the interactive version of Git Rebase. Nice job in making it through these first videos. You now know how to create a pull request on GitHub, how to update a pull request, and squash changes. These tools are all super helpful when using GitHub. Up next, you'll find a reference of the commands we used and links to where you'll find more information. After that, there's a quick quiz to check that everything's making sense. GitHub and other repository hosting services offer tools for doing code reviews on their platform. And while this is called code reviews, we can actually use the same tool and process to do reviews of any text file, including configuration and documentation. Doing a code review means going through someone else's code, documentation, or configuration, and checking that it all makes sense and follows the expected patterns. The goal of a code review is to improve the project by making sure that changes are high quality. It also helps us make sure that the contents are easy to understand, that the style is consistent with the overall project, and that we don't forget any important cases. Reviews increase the number of eyes that have checked the code. This increases the code quality and reduces the amount of bugs. It doesn't mean that there'll be no bugs, but at least the most obvious bugs will be caught. Also, this helps spread knowledge, since both the code writers and the code reviewers now know what the code is doing. When we work in the same office as our teammates, We can do reviews in person by looking together at the changes and discussing how the contents fit together. But when the person that we're working with is in a different office or time zone, we're better off using a code review tool. Code review tools let us comment on someone else's code. This lets us leave feedback on how they could make their code better. Common code issues are unclear names that make the code hard to understand, forgetting to add tests, or forgetting to handle a specific condition. If we're writing documentation, our reviewer can help us catch typos and things that aren't totally clear. On platforms like GitHub, it's common for projects to only require reviews for people that don't have commit access, while the project maintainers can commit directly. But doing code reviews improves the code's overall quality. Today, some open source projects and lots of companies require code reviews for everybody. This isn't because they don't trust them, but because they want the highest quality code. And code reviews are how they get there. One thing to always remember, code reviews are not about us being good or bad coders. They're about making our code better. And not only that specific review, but in general. By getting feedback, we can keep improving our code techniques. And by reviewing other people's code, we can also learn new and different ways of achieving results. Like everybody else, after toiling for hours on a problem and finally solving it, all I want to do is submit my code and be done with it. But this rarely happens. Code reviews usually send me back to the drawing board with small errors and nitpicks. But that's a good thing. These code reviews point out things that we might have missed along the way and ensure that our code makes sense to others. One example that springs to mind is back when I was writing a script for an Android bug report parser. After hours of fiddling with the code and writing tests to back up what I did, I finally sent it to a code review and thought I was done. Turns out I had a bunch of little style guide errors that my reviewer wouldn't let me get away with. More importantly, while fixing the style errors, I noticed that I had forgotten a major use case in my script that would have stopped my code from working. So I fixed both the style errors and the missing use case and could submit my change with a smile. At Google, we believe deeply in the value of reviewing everything we do. Even the contents of these courses have been reviewed by lots of people. These reviews make sure that the contents make sense, are technically correct with no significant gaps, and follow the established guidelines. Shout out to my colleagues for keeping us on our toes and making sure that these videos are top rate. Up next, we'll talk about the typical reviewing workflow and how to get the most from the review process. In our last video, we explained what code reviews are and how they can make our code better. Now, we'll check out a typical code review using a reviewing tool. Imagine we've just finished a bunch of code changes. Now we'll ask a reviewer to look at our code. The reviewer might say that everything is okay and our change is approved, but usually they'll find something that needs improving. So they'll add comments to our changes explaining what needs to be fixed and how. When we get the review comments, we'll address them by fixing our typos, adding any missing tests, and so on. After addressing a comment, we can mark it as resolved so that we know it's been taken care of. If there's something that we aren't sure how to do or we think a different approach might be better, we can reply to the comments and ask our reviewer for more information without marking the comment as resolved. Once all comments have been resolved and our reviewer is satisfied with the results, they'll approve the change and we'll be able to merge it. You might be wondering, what are all these comments that I'll receive? There's a wide range of things your reviewer might have to say about your code. Sometimes you might have forgotten to take into account something important and you'll need to do significant work to fix it. Sometimes your reviewer might point out something small that's not really critical and the comment is mostly a suggestion for making the code better. These comments are usually prefixed saying that it's a nit. Whatever it is, it's important that you take the time to understand what the comment is and what you need to do to address it. For example, if you've written a piece of code and your reviewer asks you to explain why or how the code is doing something, it might be tempting to just answer their question in the comment and mark it as resolved. But this isn't a great idea, because only the reviewer gets to see your answer. Instead, it's better to take this as an opportunity to make the code clearer. For example, you could do this by using better variable names or splitting a large piece of code into smaller functions. On top of that, you can add comments to the code and documentation to your functions to make sure that the how and why are clearly explained. It's common for code reviews to include several comments about the style of the code. To avoid a lot of back and forth, it's a good idea to refer to a style guide that explains the preferred coding style for the project. For example, lots of Python projects use the PEP8 style guide. If the project you're contributing to doesn't include a style guide, make sure that you ask for one. And in case you need inspiration, we've included links to some common style guides in the next reading. There are a bunch of code reviewing systems out there, and while they all follow the same patterns, they don't all work exactly the same way. In some code reviewing tools, you'll need one of the project maintainers to approve your code before it's submitted. In other tools, you'll just need to get a couple +1s from contributors to the project before you can submit. The goal is to always ensure that your code has been reviewed by people who are familiar with the project so that it's ready to be submitted. Can you think of a project you've worked on in the past where code reviews could have been helpful? Maybe you worked as a part of a team and had trouble making sure that everyone agreed on how things should be done. Or maybe you were learning how to use a new tool and you would have benefited from a second pair of eyes on your work. No matter how simple or complex a project is, it can always be improved with good code reviews. Up next, we'll dive into how this code reviewing process works on GitHub. Up till now, we've talked about the general process of doing code reviews. This process applies to any platform with code reviewing tools. Now, let's check out how this process looks on GitHub specifically. Remember, a while back in this module, we created a pull request that added a README file. Conveniently, our colleague just replied with a few comments. Let's have a look. The code review has one overall comment, and line by line comments highlighting the things that we need to get done. We can view all changes requested for the file we created by clicking on the View Changes button. Our reviewer made 3 comments about our file. The first one is asking us to add a period at the end of the sentence. The second one asks us to add another hashtag, which will make the title render in a smaller font. The last will require a bit more work, since it's asking us to include a couple more examples. Let's fix these. We'll add a period at the end of the second sentence, and then add a second hashtag before the example title, and finally add a few more examples. To do that, we'll use the star character, which is another feature of the Markdown language that lets us easily create bullet points. So we'll add a couple more lines with the same format and say that Hopper, Grace M turns into Grace M Hopper, and that Voltaire stays as Voltaire. Alright, we've addressed all the comments in our code review. Let's save our file and then commit the changes. Since we want this change to be a part of the previous commit, we'll call git commit-a with the --amend flag, which will edit the original commit. Once we've done that, let's call git status to see what Git has to say about our repo. Just like before, we see that our change has diverged from the origin/master branch. You might remember that git commit-amend modifies commits, so it's not safe to do with commits that have been pushed to the repo. Using amend is pretty much the same as creating a new commit, and then using an interactive rebase to fix up a change. So the commit gets replaced by a completely new commit with a completely different commit ID. This means that to push it, we'll need to use the -f flag again. Remember that forcing pushes is fine for pull request branches because nobody else should have cloned it. But this isn't something that we'd want to do with public repos. All right, we've done what our colleague asked. Let's now go back to look at the pull request and resolve the comments. See that comment that says outdated? That's because we've pushed a new version since we've made the change. But since we've taken care of the request, we can ignore the outdated comment and just resolve the conversation. Cool. We've addressed all the comments. We can leave a message in our conversation to let our reviewer know that we've resolved all the comments and ask them to take another look. Our reviewer can now check out the new changes and approve them if they're satisfied. As with lots of other topics we've covered, making the most out of the code review process will require some practice. It's great to have some tips, but in the end, we need to learn by experience. So don't be afraid to practice, practice, practice. Up next, you'll find some resources to learn more about code reviews and a quiz to put this knowledge into action. After that, you can try out doing a code review on GitHub. Over the past few videos, we've looked at how we can collaborate with others using tools provided by platforms like GitHub. These tools can be very helpful, but some coordination outside of the platform is always going to be needed. For example, the project you're working on might need a medium or large refactor that will affect multiple lines of code across several files. It's important to give your colleagues the heads up that this refactor is coming. If possible, try to do the refactor while the other developers are working on a different part of the project, because this helps avoid large and complicated conflicts. We've called out a bunch of times that documenting your work is super important. When working together with a large group of people, documenting what you do and why you do it becomes even more important. Otherwise, you'll spend most of your time answering everybody else's questions. Also, say there's a problem with your service while you're on vacation, or the person who developed the code is on the other side of the world and currently sleeping. In these situations, the documentation needs to be good enough to help someone else fix the problem. The most basic form of this is writing clear code, with good comments and documentation for those functions in the code. On top of that, you'll want to create documentation files to let others know how they can interact with your project, like the readme.md file that we created in an earlier video. If you're a project maintainer, it's important that you reply promptly to pull requests and don't let them stagnate. The more time that passes until a pull request gets reviewed, the more likely it is that there's a new commit that causes a conflict when you try to merge in the change. On top of this, if the person contributing the change is a volunteer that's just trying to help, they may lose their motivation to work on the project if you make them wait too long for feedback. Another thing to remember when you maintain a project, especially if it's an open source project that volunteers are contributing to, is that it's important that you understand any changes you accept. You never know if the other person is going to stick around to maintain the code after you merge it in, so you better make sure you can do that. You should also be careful with which patches you accept or reject. Accepting everything that gets sent your way might make your project grow too much and become unmanageable. Or it might take into account too many corner cases and cause complicated code that's hard to maintain. On the flip side, if you don't accept any pull requests, you'll discourage contributors and miss out on keeping your project active and relevant. We've talked about style guides a few times already. If you're contributing to a project, you'll want to check out the style guide and make sure you follow it. If you own a project, it makes sense to create a style guide so that others know what you're expecting from them. In our next reading, we'll include links to some of the most common style guides and pointers on how to include a style guide in your own project. When it comes to coordinating who does what and when, a common strategy for active software projects is to use an issue tracker. This is a super useful tool, and we'll find out more about it in the next video. On top of that, when the project is large enough, it's important to have another way of communicating and coordinating between contributors. For many years, most projects use mailing lists and IRC channels for communication. Recently, new forms of communicating have gained popularity, like Slack channels or Telegram groups. If you're managing your own project, choose whatever communication medium best fits your needs and those of your contributors. If you're collaborating with a project you don't own, you'll want to find out what channels are being used for collaboration. And with that, you now have a rough idea of how to collaborate with others across the internet. Up next, we'll talk about two important tools that can help us collaborate better: tracking issues and continuous integration. Deciding who's going to do what is critical when collaborating with others. With no coordination, two or more people might spend time working on the same part of the project, while nobody works on the other critical parts. Imagine that you and your colleagues decided that you'd work on building automation software for keeping the computers on your network up to date. But then instead of dividing the task into smaller pieces and assigning them to different people, you just randomly started working on some part of the infrastructure. The result would probably be total chaos, with different pieces of software that won't work well together and lots of gaps that nobody worked on. For small teams, it's usually easy enough to discuss in person who's going to be working on what. But as soon as the group starts growing, talking about responsibilities and what to do next becomes more of a hassle. That's when a tool like an issue tracker or bug tracker can help us coordinate our work better. An issue tracker tells us the tasks that need to be done, the state they're in, and who's working on them. The system also lets us add comments to the issue. These comments can be super helpful. They can give us more details about the problem, explain a way to solve it, or detail how to test if it's been solved. Issue trackers aren't just useful for people actively working on projects. They also let users report bugs when they come across them, even if they don't know how to solve the problem. Sometimes users come across problems that we never even thought possible, and having them report these issues through a bug tracker can help make our projects better. And the tracker can also help volunteers that want to start contributing to the project. Having a clear, visible list of the pending work lets new contributors figure out how to help and where to jump in. There are a bunch of different solutions to track bugs or issues. There's a popular bug tracker called Bugzilla, which is used by quite a few open source projects. On the flip side, platforms like GitHub have an issue tracker baked in. So, if you're hosting your project there, it can be very handy to track work on your project, like the problems to solve, the features to add, and the use cases to include. Let's check it out. This is the list of issues for our health checks projects. For now, it only has one issue asking us to update our documentation. One of our colleagues suggested that we create a new health check that verifies if there are any critical error messages inside the system logs, like kern log or syslog. Errors that appear there might help troubleshoot some interesting problems. So, this sounds like a good idea for a new check. Let's create an issue for this feature by clicking on the New Issue button. For the title of the issue, we'll say that we want to check for critical errors in system logs. And for the issue's description, we'll say that the new check should go through var/log/kernlog and var/log/syslog and check if there are any critical errors that need attention. When writing an issue's description, it's a good idea to include all the information that we have about the problem or missing feature, and any ideas on how to solve it. And if new information comes up later on, it can be added as additional comments on the same issue. Great, we're now ready to submit the new issue. Okay, we now have the new list in our list of issues to solve. The issues in the list all have numbers that identify them. As we called out in an earlier video, in GitHub, each issue or pull request in a project has a unique number associated with it. So, if we have a pull request with the ID 5, there won't be an issue with ID 5. GitHub will automatically reference issues and pull requests and comments when we mention them using the hashtag number format. For example, if we use hashtag 2 in a comment, it will automatically reference the issue we just created. If you're fixing an issue through a pull request, it's possible to automatically close the issue directly once the code is merged. To do this, you need to include a string like closes:#4 in your commit message or as a part of the description of your pull request. Once the code gets merged into the main tree, GitHub will automatically close the issue with a message linking it to the new commit. Let's try this out by updating the documentation like the hashtag 1 issue requested. This issue seems easy enough to fix. We need to update the README file to use the new file name and explain a bit more about how our script works. Before we start working on this, let's get the issue assigned to us. Assigning issues to collaborators helps us track who's working on what. By assigning the bug to yourself, you can let others know that you're working on it so they don't need to. All right, let's update the documentation. So, we're still using the old name of the main file, allcheckspy. We renamed that file a while back to healthcheckspy. Let's change our README to use the new file name using inverted quotes to show monospaced text. Then, we'll add that this script will print everything okay if all checks pass, and it will print the corresponding error messages if something fails. We've updated the documentation. Let's save the file and commit this change. This time, we'll call git commit-a so that we can edit the commit message in the text editor. We'll say that we've updated the README to use the new name of our script. And in the longer description, we'll add that we've included more info about how the script works. Finally, we'll wrap up by adding the string closes#1 so that the issue will get automatically closed once this commit is integrated into the main tree. Our commit message looks good. Let's save it and push it to the repo. Now, let's go back to the issue that we were addressing. We see that our issue is automatically closed with the commit we pushed. We can click on the commit ID to see the full commit. So here's the commit message we created with the associated change. See how the hashtag 1 that we included as a part of the commit message is automatically detected as a link to the hashtag 1 issue? There's a bunch more to learn about tracking issues, but this should be enough to get you started. Feel free to experiment on your own and try more ways to interact with the system. Throughout this course, we've been making changes to our files. Sometimes we ran them manually to test if they still worked after the change. Sometimes we just forgot to do that. This is common for any software project, no matter how big or small. As humans, we're not great at remembering to do lots of stuff. So we can't rely on people remembering to test their code, not even ourselves. Luckily, we don't need to. We can write automated tests to test the code for us, and then use a continuous integration, or CI system, to run those tests automatically. A continuous integration system will build and test our code every time there's a change. This means that it will run whenever there's a new commit in the main branch of our code. It will also run for any changes that come in through pull requests. In other words, if we have continuous integration configured for our project, we can automatically run our tests using the code in a pull request. This way, we can verify that the tests will pass after the new changes get merged back into the tree. And that means instead of hoping our collaborators will remember to properly test their code, we can rely on our automated testing system to do it for us. Once we have our code automatically built and tested, the next automation step is continuous deployment, which is sometimes called continuous delivery, or CD. Continuous deployment means the new code is deployed often. The goal is to avoid rollouts with a lot of changes between two versions of a project, and instead do incremental updates with only a few changes at a time. This allows errors to be caught and fixed early. Typical configurations include deploying a new version whenever a commit is merged into the main tree, or whenever a branch is tagged for release. There's a large world of tools and platforms related to CI/CD, which is what the whole system is usually called. One popular option is Jenkins, which can be used to automate lots of different types of projects. Some repository hosting services, like GitLab, provide their own infrastructure for doing continuous integration. GitHub doesn't offer an integrated solution. Instead, the popular alternative is to use Travis, which communicates with GitHub and can access the information from GitHub projects to know which integrations to run. No matter which tool you use, there are a bunch of concepts that you'll need to deal with when creating your own CI/CD. The first one is a concept of pipelines. Pipelines specify the steps that need to run to get the result you want. For a simple Python project, the pipeline could be to just run the automated tests. For a web service written in Go, the pipeline could be compile the program, run the unit tests and the integration tests, and finally deploy the code to a test instance. Another concept that turns up when doing CI/CD is artifacts. This is the name used to describe any files that are generated as part of the pipeline. This typically includes the compiled versions of the code, but can include other generated files, like PDFs for the documentation or OS-specific packages for easy installation. On top of this, you might want to keep the logs of the pipeline's build and test stages to review if things fail. When setting up CI/CD, we have to be careful about how we manage secrets. If our pipeline includes deploying a new version of the software to a test server, we'll need to somehow give the software that's running the pipeline access to our test server. There are a bunch of different strategies to do this, like exchanging SSH keys or using application-specific API tokens. For some pipelines, it might be unavoidable to use one of these methods, but be aware that you're giving access to your test servers to the owner of the service that's running the pipeline for you. It's a bit like giving your house keys to the person checking your heating once a year. So, 2 things to remember. First, make sure the authorized entities for the test servers are not the same entities authorized to deploy on the production servers. That way, if there's any kind of compromise in the pipeline, your production server is not affected. Second, always have a plan to recover your access in case your pipeline gets compromised. If you want to set up Travis for your GitHub project, you can do that by logging into the Travis website at www.travis-ci.com using your GitHub account. Then enable the projects that you want to continuously integrate. After that, you'll need to add a configuration file to your project, written in YAML format that states the language your project is in and which steps to take for the pipeline. This file can be very simple if your project follows the typical configuration for the language you're using. But it can also become very complex if you want to run a complicated pipeline with lots of stages and steps outside the default. We won't go into a ton of detail here, but there's more info in the next reading coming up. Feel free to read up on it and investigate on your own if you want to continuously integrate and deliver your project. Yes! You've made it to the end of the last module. No, seriously, congrats on making it all the way here. Wow, we've learned so much over the last few videos. We've checked out a lot of tools for better collaboration through GitHub. We looked at the typical workflow for pull requests, like how to update and squash changes. We learned how code reviews make our code better by helping us catch bugs, typos, and other problems. Finally, we looked into some advanced tools for collaboration, like issue trackers or continuous integration services. All this builds on the other tools and techniques for version control that we've covered throughout the course, like checking the change history, rolling back a bad change, and merging other people's changes. You've learned a lot over this course, and you should be really proud of what you've achieved. The first time I used the VCS was during my first role at Google, and once I understood what it could do for me, I mainly felt one thing: relief. I was so amazed how it made it so easy to look through code and figure out exactly who contributed to the project and what they did. And if I ever had any questions, all I had to do was message the person who last touched the code and sit down with them to learn. I hope that you're also starting to experience the power of having control of your code, and that you're excited to use a version control system for all your upcoming projects. Up next, we have the last assessment in the course. You'll need to interact with GitHub to fork a repo, push to your own repo, and then create a pull request from your change. We'll include detailed instructions on all of this in the next reading. Best of luck, and remember, you got this. Congrats! You've made it to the end of the course. It's been an interesting and challenging journey, and you've done an amazing job. By now, you're practically an expert in using Git to control your code. You've learned how to track your changes, revert changes when they don't make sense, resolve conflicts if you happen to edit the same code as your collaborators, and a bunch of other techniques for effectively collaborating with others. I hope that you enjoyed the ride. I know I did. For me, I find that having the change history always available is the most useful part of version control. This is especially handy when working with multiple people, and I hope you'll use and see the benefits of this tool too. Well, it's time to wrap up. I've really had a blast spending this time with you and sharing a little bit about my story and my passion for IT and version control. Some of these concepts were hard to tackle, so thank you for sticking with me all the way. That shows impressive commitment to learn. On behalf of my colleagues who you've met or you'll meet in the next courses, we'd like to say good luck. We look forward to seeing your code out there in the world, automating more and more stuff. During this course, we've learned a lot about version control. We discovered how we can use it to understand the history of our projects and to roll back to earlier versions if an update causes problems. In our next course, you'll learn a lot more about finding the root cause of problems and figure out how to fix them. To tell you all about that, here's my colleague Amanda, who will be your instructor. Hey Amanda, what can learners expect from the next course?
Hey there, Kenny, and hello to all our learners out there. I'm super excited about the next course. We're going to learn how to troubleshoot hard problems. We'll learn how to find a reproduction case, how to reduce the scope of a problem to make it easier to understand and debug, what to do when our computers are running out of resources like memory or disk space, and also how to deal with programs running slowly. We'll look into lots of real-world scenarios. Some of them can be really tricky to troubleshoot, but we'll learn lots of different techniques to help you understand what's going on, find the root cause of the problem, and come up with a solution. I can't wait to share this knowledge with you all. I'll see you over there.
Thanks, Amanda. And thank you, every one of you, for tuning in and hanging out with me for this course. I'll see you later.